fundamentals are extremely important, and then to see where things could be applied. So that was our goal. We kind of took that around. And we did go to Brazil. We were in Rio, and we were, I don't know, we were assuming that there was going to be a lot of Petrobras people there. They weren't. But I guess we get to see all of these here. So, so my understanding, there's 12 of the people here. 12 are
12 Petrobras. Yes.
And then you have a sequence of 9 courses then. So does this give you like a professional master's degree, or does it give you something very official?
It doesn't give us nothing.
Yeah, I don't know. Academically, I think it's just work like a summer course. It's not actually a master.
Okay.
Anything, but
It's to give us all the learning.
Yeah, it will give us a lot of knowledge to apply in our jobs.
But I can see that you're probably a lot brighter, after the first 8 courses than you were when you came. But we'll see what we can do with the 9. You're just going to go out with a real glow. Like, oh my God, learned so much. So I'm going to tell you a little bit about me, but I'd kind of like to know about you guys first, since we're going to spend the week. By the way, the material that you're going to see over the week, we actually used to put into one day. So you can see why people, when we were there for a day, thought, wow, that's a lot of stuff. And that was really one of the reasons that we thought, well, maybe we should make this into a longer course. And the opportunity came up to have it as a full-blown course here in Houston. So what I'd like to do, if I can just get you to write your name and your name, who you're working for, your email. I think we have emails for people of some sort, but we'll just kind of get your get that recorded. And then what I'd like to do is to have everybody tell us a little bit kind of about your background and maybe how you might be connected with electromagnetics, and if there's anything within the context of electromagnetics that we can try to make sure that we cover, because really we're pretty open here. We've got a lot of material that we could present, and some of them might be really interesting to you and very valuable, and others might be like, okay, that's of interest, but not really of very much value. And that'll give us a chance to kind of sort of prioritize, like which we want to concentrate on. Because I think you should take the opportunity to think about, you're not only attending a course, but you're attending a course in a way that's interactive so that you can steer the information content to make sure that you get out the kinds of things that ultimately are really valuable. And that would make us feel better too, because we don't want to just sort of spew out a whole bunch of stuff that's not particularly meaningful, but to really concentrate on things that that you could kind of connect with. So and the other thing, is that we are recording everything that we do. So there's when I talk, it will be recorded, and when you guys say something, they'll all be recorded. So if that's okay with everybody, then we'd really appreciate that. We have found that to be very beneficial when we've been traveling around the world. We gave this disc course, as I said, about 25 places. Each time it was recorded. Those things are all on YouTube. And it allows us to go back. It allows people that attended to kind of go back and see what happened. And also there's discussions that come up that then can get recorded. They can actually be very, very useful. So with that, maybe I could start at the back, and you could just tell us your name and what you do on a regular basis in your company. how you've been associated with geophysics, how you might be interested, in electromagnetics and where it might come in. And if it doesn't come in, never heard about electromagnetics, doesn't come into your job at all, that's fine. Just try to find out background. So, Louis?
Hi, my name is Luis. I work at Petrobras. I work with scientific processing. I saw something about the electromagnetics in the college, university, almost 10 years ago. So after that, I never worked with electromagnetics. So my background is not so good in electromagnetics. I basically work with signal processing and signalization.
Okay. And in your position, does electromagnetics ever come up and people talk about it at all?
Sometimes in a lecture or congress, but at work, I never deal with electromagnetics.
My name is André Nicolai. I've been working at Petrobras in marine seismic acquisition for 6 years. And well, I'm undergraduated in physics, so that's about that's what I learned on electromagnetics. It's from college. It's been a while, more than 10 years. I haven't looked into it since I'm working at Petrobras much. Basically, well, most of what I remember, we did a course when we entered Petrobras. We saw a little bit of it, but not sure if I remember much of the specific methods. But I'm interested in learning.
My name is Bruno. I work for Petrobras for 12 years, and we are at the same level. I'm starting at the company working land acquisition, seismic. Then I'm working a little bit in marine acquisition. Now I'm looking for seismic process.
And what's your background in physics also? Oh, actually, Jaja?
Oh, hi, I'm Jaja. I'm a faculty member here at the University of Houston in the Department of Earth and Atmospheric Sciences. My background is in geophysics, thermal views, inversion. The reason why I'm here is because my research involves the use of EM for applications in petroleum mining and also natural hazards like landslide. Also, I'm going to teach undergraduate level EM class this fall semester.
My name is Wes. My background is in physics. I've been working for Petrobras for almost 8 years. As the class said, we all had a course, a 1-week course at Petrobras in potential methods, but the only contact that I had was this time. I work with seismic processing.
The 1-week course in potential methods was offered within Petrobras?
Yes, with Petrobras.
Okay. I'm sorry, Andre.
My name is Andre. My background is geophysics, and I've been working in Petrobras since 2013. And it's the same of the other guys. I've been working with basically seismic, a little bit in computation, processing, but not so much electromagnetics.
My name is Vitor. My background is geophysics too. And I work at Reservoir Geophysics Group at Petrobras, especially with rock physics and 4D seismic. And I have no experience with electromagnetic methods. Just a colleague of us at Reservoir did some work with 4D CSM once a time, but I never would just watch the presentation and the work that he did. It didn't work.
I'm a geologist. I work in Petrobras since 2003.
basically with seismic methods, acquisition and processing. My background is very little about, yeah.
So my name is Mateus. My background is in geology. I work with seismic interpretation for the campus and Espírito Santo basins at Petrobras. I'm in Petrobras since 2009. I have a little work with electromagnetics since try to see the lineaments and mainly for the lineament basement, and try to see some igneous properties, so how this can affect our reservoirs. We generally try to use grav and resistivity to find some anomalies for petroleum anomalies, especially in shallow parts. And today we start to use the resistivity with gravity to help construct the velocity model in areas with a lot of sound, but not very specific. Some details about this.
And when you say resistivity, do you mean like DC resistivity?
Yes.
Yeah, my name is Cristiano. My background is geophysics. So I did study a little bit of electromagnetics at university, but I'm afraid I forgot everything. But in Petrobras, I work with marine acquisition since 2012. Actually, when we go offshore, sometimes when a seismic marine survey is taking place, sometimes we acquire electromagnetic data too. So we have, I don't know if you're going to talk a little bit of acquisition data to define. And yeah, that's it.
Okay. My name is Roberto. I work with Vitor in the reservoir geophysics group. I have a background information in physics. So yeah, of course we know a little bit of the general theory. And as the other guys, I had this initial formation. And I saw some presentations. We had one guy in our reservoir geophysics group that worked with potential methods. But it's not my daily work. I work more with seismic modeling and acquisition planning for seismic. And of course, sometimes we do plan to have also other kind of simultaneous acquisition, but I don't work with it closely.
My name is Tian Zhang. Different from you, I'm working for Chevron. Yeah, I worked for Chevron 6 years, and I'm a reservoir engineer. Yeah, so I have a bachelor degree in physics and a PhD degree in petroleum engineering. So I'm here because I have a project that related to the EM methods for exploration or subsurface surveillance. For me particularly, I want to learn more about the ground penetration radar system, and also their the wave propagation modeling, Maxwell equation, and also the signal processing for the EM.
I'm Sergio. I'm working in Petrobras since 2008. I'm a geologist and physicist as background, and a master degree in geophysics with potential method gravimetry. And in Petrobras, I started working with seismic acquisition, land seismic acquisition, and then I migrated to the non-seismic methods group. And there, I work with mostly with CSM and magnetotellurics, planning acquisition, including that acquisition we have performed between 2012 and 2014. I believe it was the biggest contract of CSM in the world, or one of the biggest, with the EMGS, where I designed the acquisitions, and I participate of the the acquisition on board as well. And nowadays I work with planning of survey planning and issues more in the part of contracts also.
Okay.
Yeah.
My name is Marcos. I'm geologist. I have an MSc degree on applied geophysics to mineral exploration, mainly magnetics and gamma spectrometrics methods. I did since 2002 as geophysicist, interpretation of geophysics, seismic interpretation for prospect generation, prospect scale. And I have contact with the Petrobras crew dedicated to electromagnetics methods applied to both regional and prospect interpretation, but not directly, only providing horizon seismic data for feasibility studies and inversions.
Oh, this is good. So of the people here, I'm just going to throw out a couple things. How many people have had some contact, let's say then, with marine CSEM? That's sure you.
Just when acquiring the data.
And well logging? In particular, resistivity logging or things like that.
It was as input for interpretation.
Yeah. Does Brazil have any oil sands? Are people connected with them?
We try. When in shallow parts of the basins without a lot of salt, and we try to minimize the risk for some location.
And would you use SAGD processes in those areas? You know what SAGD is?
No.
Steam assisted gravity drainage.
Acho que tem pessoas reservatórios de vários centros, tipo, tem no Canadá, assim. Acho que a gente não. Are you saying like a reservoir to producing these oil sands?
Right, and then
Is
what
this
they'll often
what-
do is put down twin pipes and have steam.
We're asking about the reservoir to produce oil in these sands, right?
Yeah.
No, we don't, I think we don't have this reservoir in Brazil.
You're talking about turbidites, sandstone reservoirs, or like Canada?
Yeah.
No, we don't have.
And then the use of electromagnetics to maybe get near surface structure to help with getting a better seismic velocity model. Is that ever called?
Also, we use mainly to target leads with oil bearing. We can study the anomaly in targets that the guys of interpretation seismic give to us, and they have doubts about the oil content or whatever it is. But also we also work with this called poised-salt region to convert resistivity into velocity models.
Oh. Okay. That's good. I appreciate that. So I'd like now to, really kind of start. So I've introduced you to Lindsay and Gsi. I didn't tell you very much about them. But Gsi is from South Korea, came to UBC about 5 years ago, and he did his PhD in electromagnetics, but in particular looking at something that we'll talk about more towards the end, and that's a phenomenon called induced polarization. How many people have heard of IP or induced polarization?
Just at the university a long time ago. And so Gsi is now a postdoc with me at UBC,
and then he's scheduled to go to Stanford to continue on as a postdoc there, starting in January. And Lindsay is finishing up her PhD. She's has a wide spectrum of things that she has been involved with. From the research standpoint, very much involved in electromagnetics, and in particular applications and understanding when you've got steel-cased wells. It's a very hot topic these days in the oil industry. And it's a very challenging topic from the point of view of really being able to numerically compute what the fields and fluxes are, and just to see how you might make benefit of that. In addition to that, she, along with Sahi and another person from Kaka, have been instrumental in developing our whole sort of software environment, something called SimPeg, that will allow you to have all of the bits and pieces for doing scientific computational computing, forward modeling, simulation of various kinds of physical phenomena, and then doing the inversion. And then all of this is open source, and so we have a very active group in trying to make everything that we have available, and also get people like Jaja contributing on board so we actually develop a bit. So Lindsay's finishing up her PhD, and then she's going to start a postdoc at Berkeley with the Jupiter group, starting in probably October sometime. So anyway, that's our background. I'd like to thank, first of all, University of Houston, particularly Dawn, for kind of inviting us to set something up, and Edwina for all the work that she's done here. So maybe as an introduction, I'll tell you a little bit about myself. So I went as a graduate student to Scripps Institute of Oceanography. And there I was mentored by a couple of people, in particular Bob Parker, Freeman Gilbert, and George Backus. How many people have heard those names? George, yeah, okay. So George Backus and Freeman Gilbert were, I think, the real pioneers for the development of the geophysical inverse problem, really understanding that, okay, we've got a finite number of data, and we're really trying to find functions underneath that are representative. Bob Parker was a young professor when I came to Scripps, and he was the person who was really instrumental in kind of translating some of the stuff that Freeman and George Backus had done into kind of stuff that everybody could use, and went on to kind of continually pioneer things. So I had the privilege of working with all three of these people and being mentored by them, and really being at the place where geophysical inverse problems were really being developed. I thought you might be interested in this timeline. So this is years in this direction, and in 1975, if you looked at, okay, what kinds of problems can we really solve from the point of view of the inverse problem? We could handle like a 1D DC resistivity or magnetotelluric problem, maybe had 50 variables in it. And as time went on, computers got better and algorithms got better. So by the time we get to 1985, there was the introduction of the workstation. Probably a bit before your time. At that point, we could solve problems that maybe had 1,000 variables. And that allowed us to do a 2D DC resistivity and IP. By 1995, we were actually able to solve a 3D problem. And again, it's the simpler problems, the potential fields, the gravity, the magnetics, the DC resistivity, and the IP. But now we're getting up to about 10 to the 5th variable. problems. By 2005, both with the development of better algorithms and faster computers, we're actually able to solve the 3D frequency domain EM, so that's the F, and the time domain EM with a few sources. Then there's two really, really big advances that happened. The first was something called direct solvers. So you've got a big matrix system, AX equal to B. And the questions are like, how do you solve this thing? And traditionally, most of them had been sort of iterative solvers. But at some point, somebody realized, like, oh, wait a minute, I can take this matrix and factor it. And then now I've got the factors, I could go ahead and solve for many sources just using the factorization. So that gave us direct solvers. And then you have multiprocessors. Those are the two really big things that now allow us to solve really very large-scale problems. So we can solve problems with millions or perhaps in some cases up to 10 million variables and thousands of data. And that's kind of where we are. Last year, 2017, we presented the disk, which tried to encapsulate all of this background and kind of show where we are and the applications. And so here we are, really right now. So I think the takeaway thing with this at this point is that with the advances in computing power, our understanding and better advancements in the inverse problem methodology, we can actually now really solve, I think, virtually every electromagnetic problem out there that there is. So that's really good. Okay, so now you kind of need to know where you are, and we're at a position where now we no longer have to be scared, like, oh my God, that problem is just too hard to solve. We can solve it. So what are the things that have really kind of led to this thing? So first of all, there's instrumentation and data. And we've had huge advances both in the numbers of data that are obtained as well as in the quality of data. So we really have data that unprecedented quality and quantity. And here's a couple of images. This is a large-scale groundwater study. So this was a DC resistivity section that we're looking at here. So this is electrical conductivity, and this is California, so large scale. Australia is doing an MT survey that's basically covering the whole continent. And we'll talk about this. There's a hydrocarbon de-risking. This is a control source EM that involves big long stream, 8 kilometers of cable and multi receivers, pulling along over this and going ahead and ultimately inverting it. So the point about this is that there's really large-scale problems out there with large amounts of data, and that just sort of resets your vision for what needs to be solved. The other important thing that's happened is that we now have a large number of open source resources. And this is going to be a continual theme for this whole week. It's just the power that exists because people can contribute, and collectively we can march forward as a group much better than just we can individuals. So all of these web resources just allow us to collaborate, allows us to share. We can, you can do something, and we can test some changes, and we can just, do interactive computing. And there's a number of ways that can be facilitated. We've developed something called SimPeg, which is a simulation version for parameter estimation in geophysics. And then there's a whole bunch of tools out here that can be worked with. There's whatever language you're working with. We do a lot of Python, but you could do something else. And then there's things like GitHub, which allows you to store what your codes are or your data, allows people to interact with that. And then, of course, there's Jupyter Notebooks, which we'll see today. It's an interface that allows you to have in front of your screen an ability to both type words and background, as well as equations, as well as to encode, have coding there, as well as pictures, and have reproducibility. Just something that really allows the research or communication to be carried out. And we also have many applications. Now, we just travel around the world with electromagnetics, and every time you parachute into a different country, there's a whole host of different problems that are concerned. I mean, for some places, minerals exploration is, you had mentioned that. Some places it's contaminants, people dumping nasty stuff in. Water is just a big issue everywhere. Geothermal power of interest in a lot of places, especially these days when we realize we need to get off of hydrocarbons. Geotechnical problems that arise, slope stability, hydrocarbons, which is of the main interest here, or there's other things like unexploded ordnance. I guess the point about this is that we are confronted today as a society with a whole host of problems, and electromagnetics can play a role in solving these things. So that's basically it, right? So what have we got? We got the problems. We've got high quality data. We have the ability to invert any of the EM data sets, and we got the web tools to communicate, right? So, I mean, we should be there. So what's the roadblocks? Well, this is probably it, and there's a lot of them. And I think probably individually here, each person could probably resonate with some of them. But first of all, in general, most geoscientists, first of all, they don't realize the role that electromagnetics can play in solving their problem. It's just foreign to them. They just don't kind of connect with them. And they don't understand the technique. The jargon, the terminology that's used, it's got new words, it's confusing, and it seems complicated and unintuitive. This is why seismic is so nice, right? Because seismic, it's just intuitive, right? You put a blast off, there's a pressure pulse that goes off, it reflects off, at some places there's an acoustic impedance contrast, comes back, and like you see it, you got it. It's not complicated. Electromagnetics is not that way. It's unintuitive. So those are, I mean, that's a roadblock. There's another one too, and that is, well, what's the connection between my problem and the physical properties that are involved in electromagnetics? Because that's the link, right? You need to understand what that is. And then even if you do that, then okay, there's a whole bunch of surveys. Which one do I want to choose and why? Should I use a DC survey where that's when you were talking about resistivity, that's usually what's referred to? Or should I work with something in frequency or time? Okay. Should my surveys be done in the air, in the ground, underneath, right? And then what do I expect for resolution? So you're talking about ad rock, right? And then I think lastly, and this, I think for any practitioner, this is one of the things that's really most important, is that, are there situations that are similar to mine in which EM has been applied, right? Because if you have a problem and you can find out like, oh, somebody else has been working on a similar problem, they've done this kind of a survey, this is how they did it, and they've got some good results out, you're starting to feel better. They've taken the risk, and you're in much better shape. So what are the real goals of this course? Well, these are the roadblocks. What I'd like to do, what we'd like to do by the end of this week, is basically cross those things off for you. so that you kind of know where you stand, and you're just not intimidated by any of these things or limited because of lack of understanding. So our goal here, excuse me, is to kind of take advantage of, I think it's a perfect storm, really. I mean, we got the problems, we got high quality data, capability to invert, and web tools to communicate. So let's just put it all together, and that's our goal. So here's our goals. First of all, we'd really like to inspire you to use electromagnetic geophysics, and we can do that by just seeing a variety of potential applications and to look at the effectiveness through case histories. So we're going to have a number of case histories that illustrate. Build a foundation, understanding the physical principles of EM, and to be able to kind of explore and visualize what the fields are and fluxes. And we're going to have interactive apps. That's why we've asked people to bring laptop if they have. And we see that most people have. And for those, I think we've got enough that we can just kind of double up a little bit. So that means that we can stay in this room. We don't have to go to it. And we've got open source resources, EM GeoSci, that we will make use of, and you can also make use of. I want to again kind of emphasize the importance of understanding the foundation. If you remember about 15 years ago when marine EM kind of came on, there was just such a hype and such a huge expectation. And it was, part of that was actually the buy-in by really high levels of management who saw very nice pictures of electromagnetic waves going in, bouncing off of something and coming back, putting everything in terms of seismic jargon so that these big CEOs could understand, like, oh yeah, I got that, sure, and then promising all kinds of stuff. Overselling because people just didn't really take account of things, and you see what happened, right? It gets oversold. There's this huge enthusiasm. There's this big rush into it, lots of money, and then you don't meet the expectations. And the moment you don't meet the expectations, then okay, people who were really on board are now they're your most negative advocates of this thing, and so it's important to do that. So set realistic expectations. You can't do that without understanding the fundamentals. And the other thing that we're hoping to do, and this was a major thing for the discourse, was really to develop a community. Geophysics is small. Electromagnetic geophysics is really smaller. Look at Petrobras. What do you got? You've got sort of the non-seismic group. Okay, how many geophysicists are there in the non-seismic group?
9 geophysicists.
9 geophysicists.
Out of 700.
Out of 700, right. And out of the non-seismic, okay, how many of those are in potential fields?
Well, 90, but half is in electromagnetic and half in potential method gravity.
Yeah. Okay, so now you take 9 out of 700, you take 5 of them and you put them into gravity and magnetics, and then you take the other 4 of them, and they're supposed to cover all of electromagnetics. That's a tough thing. Okay, so would it not help if at least those 4 people had access to a community of people that they could interact with, ask questions, and proceed forward. So we're trying to develop that, and we'll talk more about that, and capturing case histories worldwide. This was the other thing for the disc. We actually had it in 2 days. The first day was the disc course, where we had all this material. And then the second day was something we called Disc Lab. And for that, a part of that day was for us to go to you and say, look, give us a 5 or 10 minute talk about what your problems are, what you're doing, and how electromagnetics has is involved. And this has been incredibly useful because you go to You go to India, for instance, and there they're interested in sets of problems, mostly minerals and geothermal and large-scale structure tectonics. And you go to Malaysia, there they're interested in hydrocarbons. And you go to other places, and it's geothermal energy. So capturing all those case histories has been really insightful. I don't know if there's anybody. This is a book, Electromagnetic Methods in Applied Geophysics, edited by Misak Nabigian. Is there anybody in this room that's seen that book? Fun? if you've come through any university course in electromagnetics, at least in an applied sense, this book, in a particular chapter of this book, is kind of a Bible. It's just one of the greatest chapters in applied electromagnetics that has been. It is, however, pretty dense. And you can wade through it, but even if you're able to kind of get through all the algebra, I think there's a real question like, okay, do you really understand what's going on or not, right? So what we're trying to do is to take this book and kind of make it live as an open source web resource. And what we're doing is, our effort is called GeoSci. So we'll see more of that. A major part of what we do are these case histories. We have parsed the case histories into 7 steps, and even for the seismologists, I don't think there's any person in this room that would have a huge disagreement with parsing out an applied problem in terms of 7 steps. The first one being a setup. Okay, what's my problem? Okay, so I'll do that. And then what do I know about the physical properties? So in your case, P wave velocity, S wave velocity, density, whatever, right? What am I going to do for a survey? Well, I'm going to do a 3D marine survey or whatever. What are my data going to look like? What processing am I going to do? So that's where most people are. You're kind of in here. There's a little bit up here. And then maybe you're also in the interpretation. So you're kind of in the processing interpretation part. And then there's a synthesis part. Maybe that comes more into the reservoir engineering, but you put it all together. So all of our case histories have this format. And it's kind of nice because if you parse it out like this, it actually makes it pretty easy to kind of communicate with somebody because you're succinct. You can look to see what the problem is, or you can look to see if he says, well, I'm kind of in the data part here, but you've got a context. The thing about making it live is that when we put it up, it can be edited. So you could put up a case history, and I could come along and read that, or if there was somebody else who actually knew something, they could come along and read that and say, that doesn't sound quite right. I mean, maybe we should have this. Or they could make some comments like, that looks pretty good, but should have something else. That's the point. You have something, it's live, it can be edited, it can grow. It's not static. You're going to see a lot of apps. That's why we've asked you to bring your laptops. And the question is like, why an app? What's the big deal? If you look in that chapter that I was talking about, here's 2 Maxwell's equations. Actually, this is interesting. So if I wrote an equation like this, anybody know what the upside down triangle is? How many people do not know what the upside down triangle is? Oh, good.
It's a big on side of
Okay, what about this X?
Rotation.
Yeah, curl. Okay, so grad, operator, curl, and these are fields. That's good. So anyway, so those are Maxwell's equations. They actually mean a lot, right? Physically, they actually mean a lot. But if you look at them, it's like, okay, it's an equation. What really makes that equation understandable is if you have some kind of an interface that allows you to do a numerical simulation of what's going on and allows you the ability to alter parameters. And then you start to see a picture. In fact, this picture is actually of relevance to the marine CSCM problem, because this is a current dipole that's sitting in a medium. So you can imagine your current dipole in, it's in the water, okay? And then there's currents that are going to go from one end of this dipole to the other. And yeah, that's very much relevant to the CSCM problem. So okay, so how are we going to achieve our goals? Well, use the following. So first of all, we're going to think about the application. Then we're going to select the type of survey that's appropriate for that. We're going to use the apps to explore and ask questions. And then we'll show the success through a case history. So that's kind of the procedure, and we're going to go through that time and time again as the week progresses. So as I said before, this is really a growth of the material that we had given in the SEG. And I'm actually really pleased that we could do this, because we did have a lot of material because we were pretty ambitious in what we wanted to cover. And so a day or even a day and a half was pretty short. But so now we can take that material that we presented in these various countries and just sort of open it up. As I said, the second day was a disc lab where we talked to the people about their problems. And not only is everything recorded, but we also have kind of a very nice synopsis of what's done. We have a blog, so it's given by here. And it tells you, like, the different places that we went. Like for Buenos Aires, for instance, if you clicked on there, you can look at, okay, what were the slides that were presented in Buenos Aires? And then what happened on Disc Lab Day? Okay, so who was talking? What were their problems? And then in some cases they presented talks, in most cases they did, and they were very happy to share their slides and to share their discourse. And we've got all that recorded, and it's a great resource, because what it means is you can look at this blog and you can pick up a country and you can see, like, oh, well, here's the kinds of geophysics problems that have a connection with electromagnetic. They're going on in this country. It's just incredibly valuable resource. And yeah, the whole format and images and way this is all laid out, Lindsay and Sagi have done just an incredible job. So you'll enjoy reading it. It's just kind of interesting, as well as being important. Okay, so here's the agenda for the week. And we've parsed it out into these little icons. And so they're going to help us keep on track. So the first thing that we're going to do is sort of DC resistivity. It's the oldest of the techniques. It's still used today in a variety of circumstances. And even more importantly, well, at least just as importantly, if you understand DC resistivity, then you actually understand a lot of stuff that's going to come on later on when you either frequency or time domain. So this is kind of, some people refer to that as the mother of all problems here for electromagnetic. And then we're going to do fundamentals of EM. So that is just, like, let's just look at Maxwell's equations and kind of let's just understand them a bit. Once we've done that, and hopefully we can do most of this today, then we'll look at inductive sources. And then we'll do grounded sources in time or frequency. Natural sources, somebody mentioned MT, that's where that fits in. Inverse theory, how many people have had a course on inversion? Anybody?
In a general sense, applied to sizing, many of us has done some works in size inversion or general mathematics of inversion problems, but not specific to apply to.
But if I mention the word, I'd say Tikhonov curve, with that, how many people would recognize Tikhonov curve? Okay.
Linear algebra.
What we found very interesting as we traveled around was that there was a lot of people out there that are doing inversions in the sense that they've got a software package and they're putting stuff in and they're getting images out, and so there's a lot of people that are doing that, and they actually have a lot of. If you talk to them, it sounds like, oh, they actually know a lot, because they're talking about, oh, data misfit, I'm talking about my regularization term, Tikhonov curve, and stuff like that. And then you start asking them a little bit about, well, okay, what about this? And it's like, oh, I have no idea. And so what you realize from that is that there are a lot of people that are using inversion codes, but actually don't really understand some very, very important fundamentals about what's going on. So we're going to spend sort of a half a day going through that, because that's so important. We'll look at GPR, and then we're going to look at something called induced polarization. But it's really the fact, at this point here, we're looking at physical properties whose values become frequency dependent. I mean, you have that in seismology. You've got dispersive wave propagation. So that's there. And then we'll talk about the future. This is actually a pretty ambitious schedule. There's a wide variety of backgrounds. In some places that we go, there's actually people who are, I'd consider to be experts. They've written books on things. And this kind of comes a little bit from that. But I show this just because I think it's really interesting. I go for coffee on Saturday mornings with a group of people. We've done this now for, I think it's 24 years. Every Saturday morning, 9 o'clock, same people, same jokes, same coffee shop. And when you go in, there's they write a new saying on their little blackboard. And this is what it was this one day, and I thought, well, that's perfect. And the saying is as follows. That is what learning is. You suddenly understand something that you've understood all your life, but in a different way. And if you think about that, that really is the thing that kind of enriches your understanding, because sometimes you'll think you know something and you can actually manipulate it and you can do something, maybe even think. And somebody comes along and then says, oh, but you could think about it this way. And then you realize, like, oh, that's really interesting, isn't it? Right? And now I've got two ways of thinking about it, and it just enriches you. So maybe for those people who are a little bit expert in some aspect of electromagnetics, we might still be able to find something that's interesting. Okay, so here's our global agenda. So it's kind of parsed out. So day one, we're going to do DC resistivity and EM fundamentals. Day two, we're going to do inductive sources. What we mean by inductive sources, these are any transmitter that's just like a closed loop, right? So all the airborne stuff that is done are inductive source. I'm going to show you a case history that I think you'll be really interested in. It's a time domain EM experiments in Saudi Arabia, but what they're concerned about is getting the near surface structure so that they can get a better velocity model, so that they can then go ahead and get the seismic imaging. So even though the electromagnetics is not directly finding the hydrocarbons or the structures associated with it. It's finding all the junk that's up on top and all that complicated structure, which the seismic has a very, very difficult time doing. And so now you bring that in, that helps your velocity model and makes you go on. So that's the inductive sources. Grounded sources, here's the marine EM. Okay. Natural sources, MT and inverse theory we'll do in one day. And then GPR, induced polarization in the future, one day. So that's our estimate.
Excuse me. Can I have a basic, very basic question? When I was in university, long time ago, of course, we have two kinds of big fields, let me say like that. We have the electrical methods and the electromagnetic methods. And resistivity and induced polarization, I believe it was in electric methods. Is the separation still usual, or nowadays everything is electromagnetic?
Electromagnetics, in principle, covers everything from DC to infinite frequency. But because sort of that DC part is so prevalent, it's kind of often looked at separately. But even if you actually do what's called a DC survey, you're actually putting in a time domain waveform. It's just that you're working at really low frequencies. So we have, like, our work here is on electromagnetics, but in my viewpoint, this is DC resistivity is still part of an electromagnetic experiment. You're just simply doing it at zero frequency or at a really low frequency. Most of the work that we do is going to be at kind of intermediate frequencies, maybe up to 100,000, or from 0.1 to 100,000 hertz. That's most of the stuff. But then we can get up into GPR, which is like mega or gigahertz, right? So it's all electromagnetics, but sometimes it's just kind of convenient to parse it out, like, okay, I'm working at the really low frequency and I'm just going to call it easy. So what we're going to do today, I'm going to first of all give you an introduction to electromagnetics, and then we're going to go through DC resistivity, just kind of the theory, some case histories. Then we'll have time to have you play with the apps, because I think that's where you'll really consolidate your learning. And then we'll do the EM fundamentals this afternoon. The other thing I wanted to do is we're talking about kind of connecting and collaborating. Is there anybody here that's using Slack? You guys know about this? So it's again a way of communicating. So we have it's just a nice interface that you can easily talk effectively to a single person or to multiple people when you're all kind of working on a same type of project. So we have one you can invite to join, and it's a way of also asking questions. Like if you had a question but you don't really want to raise your hand or something, you could just sort of post that as a question, and the moment that you posted it, Lindsay and Sagi would both get it, and you might just answer it, or they might say, hey, Doug, maybe we should talk about this, or what, right? So that's the way. And then, of course, ultimately, we're looking for people to contribute. I'm not sure within the context of Petrobras, that really kind of works out so well, because everybody likes to keep their stuff there. But we're looking for case histories and content. And here's where it's important that Jaja's here, because he's going to provide a lot of stuff in here for the content when he develops his course, and also in the further development of Simpeg, our software. So communicate, collaborate, go together as a community. So I'm not sure how we want to do this, but we might I just want to kind of have continual coffee is like a good idea. So let's just, and we'll have kind of continual presentations. So let's just take 5 minutes and grab a cup of coffee and stretch our legs, and then we'll do an intro to you.
Galera, a conversa vai vir, pelo que acho que foi em algum e-mail, aí tem que responder aquele e-mail confirmando a presença da vontade, não sei se todo mundo gostou. Quem não fez ainda, se ligar e... Aqui tem um link pro site, vai precisar o...
Coloca ali os convidados.
Cara...
Tem um aí do lado do
Yeah, or you can download an app.
Okay. So are you going to use the email that we put on the floor?
I think maybe it needs to go this
Yeah, so I think, no, I think we've already got the email address.
Okay, because
You'll probably understand.
because so I mean because that's my corporate email and I'm not using my computer this week, so I probably need to have my personal email in case you send like for information.
Right, so yeah, if you yeah,
Okay, so which one are you?
Aí tem o default.
So Dr. Stewart.
He invites us to.
Dr. Dan? Yeah, he should have invited you for a party maybe
Yeah.
Thursday.
Thursday. We have to confirm in that website.
Oh, sorry.
yeah, so you need to do an RSVP.
Yeah.
Just
He didn't include me because he knows that I can Well, if I can, if you can,
Foi.
if I,
So, manager.
so your manager will be for me?
Yeah.
So that's mine. Okay, I can check with Dr. Zion if there is an join, but I think it should be free.
So please, yeah.
Sorry, I don't think.
And if you have his email,
Okay, thank you.
So,
let us know if you.
We have one main guy in Petrobras America.
okay, so, sorry?
We have one guy in Petrobras that works here in Houston, the manager that works in Houston, Captain Campos, his name, that supports all of us that came to Houston. It would be very nice if we could invite.
Okay, I can
confirm it.
Okay, can I see the email?
Find it. Yes. No time to. I put this label, this color label, and
Oh,
I have no time in this last minute.
you can just search by his email here or his name. Yeah. This would have all the emails.
Yeah.
Who's organizing the Faraday event, Dr. Dan or Dr. Stewart?
Another one.
We have
Oh my God. I can find it. So I show you
So,
later.
I just need to go back to my office to drink my coffee.
But you have
I'm catching a cold.
back.
Yeah.
I'm going to back today.
I'll come back again today.
Okay,
I'll
so I'll show you.
you today in order to make sure that everything is running fine.
Okay. So I'll show you.
I'll show up again in 5 to 10 minutes.
Okay.
I get with monitor check and she told me that either graduates or generating. Okay. But she told me, they provide only the party pass for the students. So for other students, it's not included in contracts.
So where is the nearest visitor?
There is one in the garage, and in the garage, this is the first one, there's one.
In this building?
It's not in this building, but. I can show you.
Yeah.
Yeah, I think this will be.
This is the thing, right? It says a confirmation. That's not good.
Maybe you should have a link to.
Yeah, it's the other. I already clicked the link. It's the response.
Cool.
But it's not based on Dielectric to show.
So, yeah, you should have a link because in the link when you do RSTV, it counts how many people do it. But if you said, okay, thank you, and that's it, and you said I'm being there, he might forget you. But if you did the RSVP, you should be included. So we just look at the list and see how many persons that we have. Then I think.
So I would like only to know if I can pass this email for another people outside this course.
Sorry?
If I can pass this email, this link to another people to.
I told him, so you have a manager who works here in Business.
Yeah.
You would like to let him to come to this part.
Yeah.
I'll check with him and then get back to you. But
Okay.
it should be okay.
Okay.
But I will check with you. Thank you.
So, yeah, so similar size. Yeah, that's why I really want to leave that. Yeah.
Ai, caralho, como as coisas mudam. Vem aqui para baixo, centro.
No, that's not what happened.
That's ganhando dinheiro. Por essa, eu tô indo em você.
Ai! Como é que eu vou escroto, né? Olha aí como o Matheus botou no grupo.
Ah, no grupo, não aqui. Tem vídeo que eu só abro em casa.
Caralho, caralho. Olha o que os moleques fizeram. Pegaram um calango, botaram nesse foguete, velho. Olha aí. Que isso, cara? Isso é muito louco.
Tu viu aquele que me botou o laxante no pombo?
Caralho.
Lá no tomando uma chuva de cagada.
Ai, meu Deus.
Cara, é importante. O que a Maura falou lá?
Caralho.
Tá gravando, hein? Cara, eu acho que tem que falar um negócio. Max, descobre o e-mail do Carlos de Campos, do e-mail da Petrobras.
Carlos de Campos?
É, da Faraday. Vai.
Só falta a conversa mudar, você tá andando lá também.
I keep getting intrigued, but it's always interesting to look around, right, and see what's on the blackboard. So you guys for taking this course, I'm just intrigued about this plot here. We've got time on this axis, and then it's like my boss and my wife.
We give you 1 week to invert this graphic and give us some information. Oh, that's the goal. Yeah.
Okay, there's our challenge.
Big challenge. Actually, boss and wife are redundant both.
Sorry?
Boss and wife are redundant. I don't know what to say. It's quite the same.
Oh, redundant. Yeah, they're the same. Exactly.
Boss.
There's no separation. Boss, wife, yeah. Commander in chief, whatever. Okay, so we'll just do a little introduction here to. So I just throw 4 images up here, just for a little context. So this one was for minerals application, water, unexploded ordnance, and hydrocarbons. Okay, so those are 4 things, and the question is, how do we locate them? How do we characterize them? How do we get some information out about that? So there's 3 physical properties that actually are of interest here. And the one that we're going to concentrate on is electrical resistivity, or sometimes we think about it in reverse, there's reciprocal conductivity. So one of the things that you're going to get used to throughout the week is that anybody, like myself, who works in electromagnetics, we constantly flip back and forth, resistivity, conductivity, right? And we kind of do it kind of depending on sort of the size of the numbers, so that we're more or less talking about numbers that are making some sense, right? Not 0.0007, Siemens per meter. So first of all, let's just set the tone on the resistivity, which is on this axis here. First of all, it varies by many orders of magnitude. So in seismic velocities, you get a 20% change or a 50% change in velocity is like, wow, that's big. Here, we can go from 0.01 ohm meters, so that's the units. So that's very low resistivity, which means current passes through something very easily. That could be massive sulfides or graphites or salt water. All the way up to 100,000 or even more ohm meters, which could be like igneous rocks or limestones or permafrost. But that is 8 orders of magnitude. Those really, really big changes. Most of the rocks that we're concerned with, the clays, the sands, the gravels, the tills, they all span a couple of orders of magnitude in the values of the resistivities. The reciprocal of resistivity is conductivity, so that's plotted on the bottom. So anything that's has a high resistivity has a low conductivity, and vice versa. Conductivity, the units will be Siemens per meter, or sometimes millisiemens. So that's basically electrical resistivity. From the point of view of Petrobras people, anybody else, this is kind of the area that we're interested in. Hydrocarbons, kind of 100 ohm meters. That's what we're looking. If you have fresh water, could be playing in that. Salt water is really much more conductive. So a lot of the things that you're worried about in hydrocarbon discovery, whether is this an oil or is this a brine, makes use of the fact that the oil is up here and the brine or salt water is way down there.
Is it pure salt water or rock saturated by salt water?
The final conductivity is going to depend upon how much salt water you have in there, what the conductivity of that water is, if it's pure salt water or whether it's dilute, and then just what the fabric of the rock is and what the pore space is and what the fluid saturation is. So it's kind of variable if you take a rock as to it. But generally, you take a rock, put some salt water in it, it's going to be more conductive. If you get rid of that brine and you're replacing it with hydrocarbons, then it's going to be more resistive. And that really is the diagnostic indicator for the marine EM. The second physical property is something called the dielectric constant. More technically, it's the electrical permittivity. This is appropriate particularly in higher frequency work, for instance, the ground penetrating radar that you're interested in. And this is a property that has less dynamic range, basically goes from 1 to 80. So the relative permeability or dielectric constant in air is 1, fresh water is 80, and actually salt water is also 80. So whereas conductivity depended a lot on how much salt is in, the dielectric constant doesn't depend upon the amount of brine at all. And then other things can vary between 1 and 80. So that's dielectric constant. We're not going to actually talk about that till the very last day when we do DPR. The other important magnetic property, we're not going to talk very much about it, but actually is the magnetic permeability. For many cases that we're interested for sort of minerals applications or things like that, we actually reduce it to magnetic susceptibility. Basically, it tells you how easy it is for a rock to get magnetized under the influence of an external field. And again, you see things vary in a logarithmic fashion over well, 6 orders of magnitude. The really high magnetic materials, something called magnetite, sitting way up here. Whereas if you get down to metamorphic rocks or sedimentary rocks, they've got a very low magnetic susceptibility. But magnetic methods play a huge role in, say, mineral exploration, or in the hydrocarbon industry where you're trying to look at large-scale structure. You use gravity and magnetics, and so that really is part of Maxwell's equations. We tend to use it at that low frequency, at that kind of DC limit, right? In which case it kind of takes a range onto itself, but it belongs in Maxwell's equations and it's an electromagnetic.
Use, for example, for mapping dikes, which is vertical structure hard to see in seismic. So in magnetometry, this is easily viewed in map.
Exactly. Yeah, so everything's got its place, right? This is why it's important, I think, for an audience like this, just to kind of, figure out how all of these other non-seismic methods can fit in. But we're actually going to stick with just the electromagnetic part. So here's a cartoon that sort of sums everything up. We've got some kind of source that's going to put energy into the ground. And we've got these 3 physical properties: conductivity, magnetic permeability, and electrical permittivity, epsilon. And energy goes in. As it propagates through the Earth, it depends upon what these physical properties are. And then we get some data that are obtained back. So here's Maxwell's equations. It's basically a non-mathematical course, but on this particular slide, it's kind of amazing, actually, if you think about it. But on this particular slide are a set of equations that basically govern a large section about how the world works in this case and how we operate as a society. Because whether you're talking about the lights, or whether you're talking about your laptop computer, or whether you're talking about anything that's connected with electronics, you're talking Maxwell's equations. So here's a set of equations. And let me just kind of run you through. So remember this curl operator. It basically is kind of like a circulation. And basically what this equation does is, so this is a magnetic flux on the right-hand side, and this is a time rate of change of it. So this equation is saying, okay, I've got a time rate of change of a magnetic field, and that is going to be related to an electric field, but this thing here is a curl operator. So somehow there's going to be like a time-varying change of magnetic field, and it's going to give me some sort of an electric field that's going like that. So physically understanding what can be obtained through that. And then so that's called Faraday's law. We'll go into these things in detail, but this just kind of gives you an overview. And the same is true of this with Ampere's law, which I think you're all familiar with. And that is, if you have a current, then that gives rise to a magnetic field. So here we've got current density J gives rise to magnetic field. So these are equations in the time domain, and we're going to be consistent throughout the course that these will all be in lowercase. In the frequency domain, where we're thinking about everything being harmonic, that's what we call frequency domain. we're going to have the same letters, but they're going to be capitalized. There's quite a few things here. There's an E, an H, a J, a B, and D. There's only like 3 equations up here. We've got all these other fields and fluxes. There's actually relationships between these. Are called constitutive relations.
Aren't we missing the fourth? The divergence of the electric field related to electric charge?
You can actually that equation turns out to be redundant. You can get that equation just by manipulating these, but you could have del dot E is equal to rho upon epsilon. So we've got these basic equations. These are actually all we really need to work with. And in fact, so in addition to these, we need to have some relationships between a field, say an electric field, and a flux, which is a current density, or a magnetic field and a magnetic flux. So these things here are established in the laboratory, and they give us a relationship between some of the fields and the fluxes. So if we take these equations and we put in appropriate sources, so we could have sources, either electric or magnetic sources, and have appropriate boundary conditions. Because as I said, this slide summarizes up all of the possible results. What you think about is kind of amazing, right? That you can just somehow on one page write some symbols that allow you to understand how how currents are going in the brains, or magnetic fields are generating from currents in the brain, to how your car works, or how the energy is produced, and how your cell phones work, and everything. So let's just take a look then at a few things. Let's first of all talk about a source. Okay, so we need to have an energy supply. So here's our cartoon. We've got a source. So what kind of a source could we have? Well, we could have a source that looks like this. So we have a plane, and we've got a loop around here. So we could put a current in that loop. And that source is going to be called an inductive source. There's no contact with the ground. It's just a loop of wire, and there's a current going through it. The other source is grounded. So we've got some current that's going through here, and it's grounded at the 2 endpoints. So here's your marine CSEM, although this one's portrayed at the surface, but that's what it is. So you got 2 types of sources. There's inductive and grounded. Now, we could put in all kinds of waveforms for the current. Right? So we could put in a harmonic waveform. So we're going to call that frequency domain. So now you're just putting in a sinusoid that looks like that. Or you could put in a more complicated waveform, some kind of a transient, where you have something that's on, and then you turn it off. And so maybe it looks something like that. So that's our waveform. You can control whatever you want for that. So in a way, it's kind of similar to seismic. I mean, you could put out different kinds of pulses. You've got vibrators, you put out chirp types of signals, you have explosives, whatever. And then there's a location where that transmitter is. I mean, it could be in the air, as it is here, could be on the ground, or you could actually put something inside the earth so that it's in orbit. Okay, so that's the source. So what about the data? Well, what can you measure? Well, we could measure an electric field. How do we do that? We could take 2 probes and put a voltmeter in, right? So measure the voltage difference between 2 probes. That's like measuring the electric field, because electric field times a length scale gives you a volt. So we could basically measure the electric fields on the surface, and also we could measure the magnetic fields. So which fields do we want to measure? We could measure E or B, or they're either at frequency or time. Good.
So I have a question. Is only in the electrical and the magnetic field, can you measure directly? Is there any other kind of farming you can measure side the two? Like energy?
Well, you can measure the B field, or you can measure dB dt. You can measure the time variation.
Okay,
But E and B,
but that's the only two
that's
that we
it.
can measure directly.
Yeah. So Maxwell's equations just reduce down to.
But like if I want to get energy, that's kind of calculated based on.
Well, the energy that is coming out from that's associated with an electric field is related to the integral of the square of that electric. It's E dot epsilon times. And the same is true with the energy in a magnetic field. So, yeah, E and B, that's it. But you have choices about which frequencies you're going to use, or in the time domain, which times you're going to measure. And then you also have like which components you want to EX, EY.
Okay. So yeah, my next question. So when you measure it, you will measure the amplitude and also their phase.
Right. So in a frequency domain system, yeah, we'll go through this. You'd measure both an amplitude and a phase. Effectively, these numbers that you're getting out are complex, and that gives rise to amplitude. So yeah, so then which components? So that's important too, right? Because remember on your marine EM, okay, sometimes you can measure a particular component. Sometimes it's really difficult to measure other components. Generally, you measure an inline component. And then it could be like where? On the ground? Yeah. In a borehole? Up in the air? So lots of options. Oh, there we go. How do I get it off? Where is he coming from? Do I have to exit?
It's to automatically update the inconvenient time.
So a lot of options that are available. Good, thank you. So, some applications. The thing about that image that I just showed you before is that if we look at what these applications are, you find that they're all associated with, excuse me, with electrical conductivity. And so that's why we're actually going to talk primarily about electrical conductivity. But it is important to remember that there actually are 3 physical properties that are associated with Maxwell's equations. So what I'd like to do now is to actually go to DC resistivity. Okay.
Eu não sei, mandou lá no link que ele botou lá. Só para vocês verem. Do GeoSci. É, deixa eu passar.
Did you want to mention they can follow?
Oh, yeah, so that you can follow along with this.
I'm reading the...
Yeah, follow download. I can show you real quick.
Yeah.
Just because it's helpful if you want to write notes or things like that.
Yeah, we were going to get hard copies of everything, but thought that was a lot.
So if you go to GeoSci.xyz, there's this module here called Courses. You can click on that.
Sorry, can you go back? What's the sign now?
GeoSci, GeoSci.xyz.
Okay.
Okay, and then you see the courses. And then here there's a button for course material for this course here. And then right now we've got 3 sets of slides there. So those are the ones that we have today. And tonight we'll get the ones uploaded for tomorrow and for the rest of the course. So.
Sorry, what's the best word for this computer? The best word.
The best word for the computer?
Yes. Because she asked me for a best word.
Oh, okay. Marwa, do you have, or Jaja, do you know how to log on?
Are we supposed to use the same login that you use in the lab? Because we received a login and the password.
Okay, let me check.
Okay.
So the
Two computers.
Okay.
Okay. So DC resistivity, we're only going to be concerned about one physical property, and that is the resistivity or its reciprocal conductivity. I think it's easier just to talk about resistivities here, but just remember that one is reciprocal of the other, and then we'll probably flip back and forth. So why are we interested in DC resistivity? Well, there's a whole host of reasons for that. In mineral exploration, I can show you a case of that. Water flow in mines, a number of applications in hydrocarbons, groundwater problems, salinity problems, for instance, or geotechnical reasons for slope stability and just trying to understand what's going on. So there's a lot of reasons for doing DC resistivity. I showed you this plot before, and it basically indicated the range of values that electrical resistivity will take. Why does that happen? What you see here is just a piece of rock. Here's a penny for scale. That has to be an American penny because we don't have pennies anymore. We got rid of them in Canada. They weren't very useful for us. So here's a penny. This you can see that the texture of this is changing from here to here. So the electrical conductivity, if I try to pass a current through that, it's going to depend upon what type of rock this is, what this matrix is, and that. You can see that one part of this is very porous compared to the other. So how do those pores connect, and what's the fluid that's filling those pores, and are there sort of metal particles in there, magnetite, pyrite, or something like that. So even just a single rock can have a very broad spectrum of electrical conductivity, depending upon the fluids, the connectivity of the pores, and what the porosity is. So that's the reason that these bars here are so spread out. So what I want to do is kind of go through some of the basics. We're going to do a basic DC resistivity experiment, show how it kind of works, and get you to have a feeling for how the fields are and the charges and the fluxes. talk a little bit about plotting the data and inverting, talk about sensitivity and survey design. Then I'll show you a couple of case histories. So here's the basic experiment. So what we have here is a representation of a mineralized body, actually one that was in Australia. And the mineralization is this red part in here, and it's a really good conductor. It has a very low resistivity, about 0.5 ohm meters. Surrounding that is a little bit of a shell, which is also low resistivity. Sitting on top of that is a high resistive cap. It's called the Gaussian. The near surface stuff is this green. That's actually a low resistivity zone too. And then the background, this host rock, is a couple hundred ohm meters. So this is sort of like 12. That's a couple hundred. This is like 400, and this is low resistivity. So that's what you're up against, and you're trying to find that. So what's the first thing that you do? Well, we're setting out a DC survey, which looks like this. It's got 2 electrodes for current. So you take a generator, right, or a battery, and you just hook it up to 2 electrodes. You pump those in, and now you're going to get a current that goes through that. And then we're going to put 2 other electrodes out here and measure the electrical potential. So we first of all set up our electrodes, and then we turn the generator on, and then we watch how the currents, well, the currents will flow through here, and they'll go from, the positive end of the generator to the negative, and so the currents look like this, and the currents preferentially flow through the conductor. That probably makes intuitive sense. The thing that we will concentrate on is that when the currents flow through, there's actually an electrical charge that's built up on the outside. So charges build up at interfaces. But now you remember now from first year physics, if we have a charge that's built up here, that gives rise to an electric potential out at the surface here, and so we could go ahead and measure that. So that's basically the idea. It's actually quite simple physically. Put the currents in through the earth, gets distorted by whatever body there is, establishes a charge buildup, and then those charge buildups through Coulomb's law gives rise to electric fields that we measure at the surface. Okay, so that's fine. How do we get resistivity out of that? That's what we're really interested in. Well, let's go back to our equations. And now in our equations, we have steady state. So now that's where DC comes in. So there's no time dependence, no frequency dependence. It's steady state. So that the first Maxwell's equation just reduces down to something that we start from here. And at steady state, there is no time varying change. So we just have things that look like this, so that the electric field is the gradient of some electric potential. And Ampere's law reduces down to something like this. Ohm's law is important. You all know V is equal to IR, right? So that's for the circuit element. Ohm's law in a continuum is like J, which is current density, is equal to sigma, which is conductivity, times electric field. So if you're going to do V is equal to IR, so sigma is like 1 over the resistance, E is going to be the voltage, and J is going to be a current. So it's like the current is equal to V over R. Okay? So if we put all this together, we get this kind of equation down here that says the relationship between a current that's putting in and the resultant voltage is obtained by solving this differential equation. It looks like that. So that's the gradient operator. Sigma is the guy that we're interested in. From our perspective, we only need to solve at this point one simple problem, and that is, what happens if we just have like a uniform half space and we plunk a current in, and then what's the electric potential going to be? Well, it turns out there's an analytic solution to that, and it says that the voltage that we get is given by this expression here, so that the V, voltage we measure, is equal to the resistivity times the current divided by 2 pi r, where r is the distance that you are from the current electrode. So we're going to use that. So here's the equation that we had, and here's what happens. So I take a current and I plunk it right in here at x is equal to 0, and then I look to see how the currents are going to go. So I think intuitively you've probably got this right. And so if I put a current in here, then currents are, everything is uniform inside the earth. They're just going to dissipate away. So the current lines would look like that. But that means that the voltage that we have is something that looks like this. It's infinite right at the current electrode, and then it decays as 1 upon r. So the voltage depends upon current divided by the distance that you're away. So if you're at this particular point here, the voltage that you measure is 6.9 volts. Okay. So how is that of any use to you? Well, we could take this equation here. We just simply rearrange it. So now we write that rho is equal to this. So if we had measured a voltage out here, 6.9, and we know what the distance is between where we're measuring and the source, that's r, and we know what the current is, we get rho. So I plug everything in here, and I get rho is equal to 500 ohm meters, which is exactly what it should have been. So this is actually, again, kind of cycle. So you have a kind of a perfect system. Just have a uniform space, plug a current in, and then just measure voltage someplace. And it doesn't matter where I'm at, Sergio or Roberto or Cristiano, that just simply doesn't matter. I just measure that voltage. I need to know how far I am away from the current source. Plug it in. I got 500 ohms. So I'm getting information about the Earth with just a single number. In reality, we can't quite do that experiment because I said if we had a generator, then we got 2 probes that we have to put in, right? We've got a positive end and a negative end. So we put a positive electrode in here and a negative electrode here, and now the current has to go from the positive to the negative. So inside the Earth, it kind of looks like this. Okay? So current looks like this. Then what does the potential look like? The potential is infinitely positive at the positive electrode, infinitely negative here, and then in between. So just the same as we were working with before, we could take a 4-electrode system, and now we have a whole bunch of R's because we need to know the R between every current and every potential electrode. We got 2 potentials and 2 currents, so we actually have 4 distances. But we could put them all in, and we say, oh, well, then if I take an electrode M, so this is going to be a potential electrode, N is the other. And so now we have a voltmeter. You have to be careful with this. So you take a voltmeter, and there's sort of like a positive end and a negative end of the voltmeter. Okay? So we're always going to make N be the positive and negative. And our voltage that we would measure by any 2 points is actually given by this formula here, which is just 1 over various R's. And we lump that all into something called a geometric factor, which is called G. So that means that we'd have the voltage be rho I times G, and we could rearrange that to give rho is equal to whatever voltage that we measure divided by this one. So if we did that for here, so we just went up and measured, then this voltage here is 2.4, it's minus 2.4, so that voltage difference is 4.8. Plug that into here, we know what these geometric factors are, and we get a resistivity of 500. Okay. So now, okay, so now my question is, this is great, but what happens if we change things and now we make like a layered earth? We put in a conductive layer or something. So, but what's going to happen? How would these currents that we have here, how would they be expected to change if I put in, let's say, a conductive layer?
Do you try to follow this more conductive medium? So the current in the shallow part will be smaller than this one.
So if I put in a conductive layer up here,
in the shallower.
Yeah, shallow, the currents would be
greater.
Greater?
Yeah.
Yeah. Yeah, so that's exactly what happens. So if I put in a conductive layer in here, then yeah, it's just an easy path, right? Yeah. So it just kind of go through there. Thing that you notice here is that with that conductive layer, this is what the voltages look like. If I put that into this formula, I get out a number of 226. So that's different than 500. But I think that should be expected, right? Because the Earth is no longer 500 ohm meters. I've got 500 below, but up top I've got 100 ohm meters. So when we use this thing, we tend to call it the apparent resistivity. So with that configuration, the apparent resistivity is 226, which is kind of reasonable, right? It's not less than 500, and it's greater than 100.
But these measurements now depends on the position that this apparent resistivity. If I put my sensors in different position, I'll have different values.
If you put the sensors in different positions, you'll have different potentials that are measured, but you also have a different G.
So
you're going to get out the same apparent resistivity. Okay. So it doesn't matter. So let's we have some apps. Okay? And I'm going to just talk a little bit about them and sort of express why they are. So we have these interactive apps, and they're going to look something like this. They're going to be sort of a visual aid for you to ask questions and to interact with things. And they're a great learning process because if you have an app, you can see you can see images, fields, fluxes, things like that. But you can also ask questions, and then you can anticipate what is what's going on. So let's see if we can fire one of these guys out. So we'll talk you through a little bit later on. I guess I need to quit. Do I need to quit this? Yeah. So actually, let me just go back. So when we'll show you how to get here a little bit later. I don't want to sort of spend too much time, but there's going to be an interface that you see that looks something like this. So it's got Gsi Apps that are sort of listed. And this is an index of all of the apps that we have available. So there's a huge number of them. So in DC resistivity, for instance, we've got a layered earth app, there's a cylinder, there's building pseudosections, there's inversions, layer cylinders, both 2D and 2.5D. So it goes on. There's also some in fundamentals. So we'll be looking at some things in fundamentals. These are just designed, we'll do those later this afternoon, so these are just designed to kind of help you understand what the EM induction process is. And then there's both inductive source and grounded source and natural source. So there's, there's a number of these. So let's just take a look at one of them. So if you, well, I said.
We still can, we supposed to have access right now to this?
No, at this point, I'll just walk you through. We'll, otherwise I think it's a bit distracting. So I'll just walk you through this, and then we're going to come back, and then we'll show you a bit more on just how to actually get to this page, how to download things, and kind of work through. But I think it's just better to kind of have a demo of what these are, and then you can, you'll have a good idea of what to expect. So I'm just going to show you what is what you'd see when you do this. There's a whole, this is all written in, it's a Python notebook, and there's a whole bunch of things up here that are called cells, and each of those will activate or carry out a particular action. There's also some text that's here, and then there's kind of widgets that you can actually work with. So this one is all loaded up. It's got some, it says, sort of investigating DC resistivity data. We're going to compute the apparent resistivity. So this formula here is something that we just showed. And now we've got this layered earth app. And the parameters that you've got are A and B. So these are the current electrode locations. And A is always the positive and B is the negative.
Make it a little bigger.
So the potential electrodes are always M and N. And M is going to be the plus electrode, N is the minus. Okay. Then there's
experiment goes inside that G factor, geometric factor you showed in the slide, previous slide.
Right. So the G is going to depend upon where the A electrode is, the B electrode, the M, and the N. So it's just all of those differences. And then we're going to have a layered space. So here's our model domain. It's going to go from -40 to 40 and 0 to 40 meters depth. And currently the A, B, and MN are listed like this. And on this slider bar, so we can move any of the electrodes. So A is at -30 at this point. If we moved it to -5, you'd see that the A electrode has now come over here. Right, so these slider bars then allow you to change all of the parameters. And so we can experiment with that. The Earth is a layer over a half space. The resistivity of the upper layer is given by this box here, which is 500 ohm meters. And the resistivity of the bottom is given by row 2, which is also 500. So everything looks just like a homogeneous half space, right? the other parameter that you have for the layer is the layer thickness. So that layer thickness could be anything from basically 0, or you could make it up to 30. But let's change the resistivity and make it, well, let's leave that. Let's just make it conductive. Now we have what we had before. So when we were working before, we had a 100 ohm meter region at the top and a 500 ohm meter region below. And we've got a thickness here of 13. I guess that's a little bit higher than what we had. If we make it 10, I think we come up to be something that looks like this. And if we look at the curve here, so here's the electric potential as a function of distance between the positive and the negative electrode. And we can see that if we measure the potentials here and we plug them into the formula, we get 193 ohm meters. So the apparent resistivity that we would obtain with this is 193. If somebody had asked if we change, like if we change the experiment a bit, so if we changed the M, let's suppose we put it back to minus 14 and we put this up to plus 16. That's right, it should change. If we invert it, it's going to come back to the same thing. But
yeah, that's a good point.
So that's the best thing, right? When you have a question, you can answer it.
Yeah.
So we have options for plotting, right? So right now we're plotting the model, right? If we wanted to plot the currents, so now you can see in this particular case how the currents are kind of flowing from here to here, and most of them are sort of confined to this top region in here. In this particular case, we're actually still plotting the the full current lines, so that they're not. It's not like the strength of the currents is blanked out or obscured by the their actual values. But here's the current density. So the current density is, we're down here, 10 to the minus 4, right? So that's in here, and up here we're like 2 orders of magnitude higher. So the kind of current lines still continue through, but most of the current is actually in that top region.
Just one point.
Yep.
Does it make sense, or do you have something like a Snell law? Because in an acoustic field, it's like a refraction. If you look at the current, as it changes the medium, you do have a discontinuity in the tilt. So do you have like a Snell law for?
Yeah, there's an equivalent of that. We'll explore that a little bit more later, but the two boundary conditions that you have is that the tangential component of the electric field is always continuous, and the normal component is discontinuous. So if you go from one medium to another, if there's something that's crossing, then the tangential has to be continuous. So that means you're going to have a different electric field on one side versus the other on the horizontal, and and then the normal component will, so it's good.
Okay.
Let's see. So that's the current density. If we can also look at the at the potentials, or we can look at the electric. So here let's look at the electric fields.
Yeah. The electric fields might actually nicely show. kind of the refraction you can see, especially
Yeah.
just below electrode A or below electrode B. You can see where that refraction.
Here, and
Yes.
it's, yeah.
Yeah, that's it.
Okay. Let's see, what else do we want to show here? Oh, I think one thing that's perhaps interesting here is to maybe, as probably to what's going next, is just to look a little bit at the currents when we change the AB separation. So let's go. So right now they're between minus 30 and 30. So if we go, let's suppose we just make this but if we put the currents really close together, so now we've got the currents here. Here's the A electrode here and the B electrode here. And you can see the current is just kind of going like this. So there's hardly any current that's coming down into this bottom region. So this is going to be an important concept. So if we've got, if we're trying to see Sergio, for instance, right? And I've got current electrodes that are simply sitting here, but kind of all the current is sort of flowing like this. So I'm just not going to see it. So I'm going to have to increase my depth of penetration somehow by continually increasing the value. And as I increase the value, so that's from -1 to 1. So if I made this -4 to 4, so now you can see how we're starting to, perhaps get a little bit closer. If I look at the apparent resistivity of this, though, it's still pretty much 100 ohm meters. So this was 10 meters in thickness. We've only got 8 meters between our positive and negative electrodes. So I'm actually still not really sensitive to what's going on in the bottom. But if I now start to make this bigger, so now if I make this -20, if I make this at 20, now I've got an apparent resistivity that's 140, right? So now I'm actually starting to get affected by this higher resistivity region below that's 500 ohm meter.
So when you increase the distance between the current poles and so on, you also increase the depth of penetration of the current.
Yes.
Yeah? And when you change the distance between M and N, which is the read, what you read, you are changing the depth of investigation also.
Well,
the MN electrodes.
So if the M and the N are really close together, we can, but we can, let's just try it. We could still get information. So right now, sitting at this, the M and the N are -4 and 11. We're sort of sitting in there. So if I was to put them really close together, and our apparent resistivity is 140, right? So if I put them at 1 and -1, so I put them at 1 and -1, I am still seeing, pretty much in that same ballpark. It was 140 before, Now it's 100 and 150. So it does change, but the driving thing in depth investigation here is really the maximum distance between actually whatever electrodes you've got, whether it's potential or currents that are coming in. And then the other thing too is if we just translate this along, in fact, we could even put them outside. So even if I have my AB over here and my MN over here, now I've got something then that is very, very close together here, very close together here. Now I'm reducing the resistivity. I'm down to 120. What was the one I was thinking about maybe looking at? So I've put my electrodes out here, MIM, MIN. So in all of these cases, you're sort of sensitive to some aspect of that boundary. It kind of changes on where everything is, but you're definitely seeing down there. If I make that layer shallower, so now it's at 10 meters. Okay, if I reduce the thickness of that layer, it's just like expanding everything out. So if I reduce the thickness of that layer to 4 meters, now we should go up in apparent resistivity. So now it's 225. So with this, with this and any 4 electrode system, the basic depth of penetration is kind of set by your overall spatial of your electrodes, and you're going to see only a fraction of that down. Often a rule of thumb is kind of like 3. So if you have maximum separation of electrodes that's 100 meters, then you wouldn't expect to see more than maybe 20 or 30 meters down. Anyway, so yeah.
I have a question. So in the figure, you show the geometry of your model, like in the Z direction, it's like 40 meters, and in the X direction, you have 80 meters. So is that the boundary you use in your model for all those calculations?
The mathematical boundary is actually larger than that, so it extends out. Okay. Yeah, because if you're solving a problem mathematically, you've got to put boundary conditions on. And,
right. So I'm asking, like, is the boundary you used in your model same as you show in the figure, which is like 40 by 80?
No, the boundary for the model is much larger. Let's see. Anyway, so that's sort of the idea. The important thing, maybe as an interlude to the next thing, is that if you've got currents that are really close together, then you're just going to sample the region that's close to you. If you move the currents farther apart, you're going to sample deeper, and that's going to give rise to what's called a sounding curve.
This experiment was the first ever made in geophysics. I believe it's the mark of the start of geophysical exploration by the Schlumberger brothers. Yeah.
I don't know whether it gets the credit for being the first geophysical experiment, but it's certainly the first EM. come on the radar screen before people realized, like, oh, you could use this. But electric methods were actually perhaps the prime choice in the very, very early stages. Let's see. So now I think with that, we can kind of go a little bit into both sounding and arrays. If there's a whole bunch of different geometries that you can use. You always have to have somehow 4 electrodes, and depending upon how you orient those electrodes, they sometimes describe different names to them. So there's something called a Wenner array, in which you've got an A and a B. There's your currents, and then you've got your potentials, M and N, and everything is equispaced. So there's the same distance in all 3 of these. And then there's a Schlumberger, which is kind of a kissing cousin to this. It's AB on the outside, and then the inside, the potential electrodes are pretty close together. So you're actually measuring closer to an electric field. These 2 things are commonly carried out, and they're used to primarily give you a what's called a sounding. So the idea is, if I'm sitting here and you can imagine that this is, it's just a one-dimensional Earth, and then I first want to see what I could see. I mean, I put the electrodes out, current electrodes out at this point, and I can see Sergio, and I put them out further, and then I can see Roberto, and then back to Nicholas. So the whole point is you just kind of expand things out, and at each expansion that you've got, you can get an apparent resistivity. So what we're looking at here is the distance between the A and the B electrodes, and here's our apparent resistivity. And if we're really small separation, the apparent resistivity stayed at 100, and as we got larger, as we saw, then currents get down into the layer, and then effectively, if the currents get really quite far apart, we actually get to an apparent resistivity that's 500 ohm meters. So this now is kind of what we had just sort of shown before. So we've got 5 meter spacings between the current electrodes, then the currents are just kind of confined to this region, and our apparent resistivity is still pretty much 100 ohm meters. If we increase that to 10, then you can see we're sort of up here. Increase it to 30, we're up here. And if we increase it farther, we'd eventually get up here. This curve that we have here is called a sounding curve. So it's just a plot of apparent resistivity against some spatial length scale. And so the idea is that somehow we're looking at, we're sort of continuing to go deeper. We get an apparent resistivity at each separation, and then that's a curve. That's sort of our data. So that's basically our the summary of our sounding curves. And the thing again to be mentioned is that if we really want to see deep, okay, then the length of the array must be considerably longer than the depth of the target that we're looking for. That's just sort of something to be kept. And as I said, something in the order, at least like a factor of 3, is kind of first order rule of thumb representative. Okay, so that gives us, so we got a sounding curve, okay, but that's just a plot of the data. What we really want to do is get a resistivity as a function of depth. So we want to somehow invert those data. So we've got our experiment, we've got a sounding curve, and now we're going to invert those data to get a depth model for electrical resistivity that is representative of what's there. So first of all, the data here that's just an apparent resistivity against some kind of pseudo depth. So we don't know how many meters anything here it is really attributed to, and we also don't know what these guys are here because they're just apparent resistivities. So that process of going from here to a depth model where this is true depth and this is true resistivity is the inversion. Spent a good part of my life looking at that particular problem. We're not going to focus on that right now. We'll postpone some of that until Thursday. But for now, we'll just simply say, like, okay, we somehow know how to do that. And in a way, this particular result is kind of a prelude to what we're going to be showing you, because here's the true Earth. It's just as we're going down, we've got 100 ohm meter over 500, and then we invert that, we get kind of a smooth representation of that. So do pretty well at the surface, do well here, and the boundary is smoothed out just because that's how the inversion actually works. So we're not going to get a precise answer, but we'll get one that's really representative. I want to turn now to a thing that is important, and it kind of comes back to this refraction business. If we, so imagine we've got this current electrode here, and we're putting it in here, taking it out here. So the current is flowing through this conductor, okay? So let's just look to see what's actually happening at this conductor. Well, first of all, it's steady state. So that means that the normal component of the current that's going in has to be continuous. So in the final solution, we looked at the current that's kind of going normal to the surface. That's continuous. Okay. And that has implications. If 1 indicates the medium on the left and 2 is medium on the right, that current density, J, has to be the same in both. But J, according to Ohm's law, is sigma times E. So that means sigma 1 E1 is equal to sigma 2 E2. And that means that if sigma 1 is not equal to sigma 2, then we've got a difference between E1 and E2. So the product of these things has to be the same. But if I change the conductivities, then that means that E1 and E2 will be different. So the answer is kind of here, but do you remember back from first year physics and the thought of like, okay, how could you make an electric field that was discontinuous? Actually, how could you do that? Look at the slide. Remember?
I have a conductor, we will have this discontinuity.
Well, if you have a change in the conductivity. So if you remember the first year physics experiment you did where you took a plexiglass sheet or something like that and just put a charge on it. You put on a positive charge and then you ask, okay, what's happening to the electric fields? Well, the electric field always goes outward from a positive charge. So if I take a sheet of charge here, for instance, and I look at the electric fields, then they're going in opposite directions. So if I cross this boundary here, then there's a discontinuous change in the electric field. Okay? So similarly here, if E1 or if sigma 1 is different from sigma 2, then there must be a discontinuous change in the electric field, and that means that there must be a charge that's built up. So that's where everything kind of comes together physically. There's a charge that's built up, and then through Coulomb's law, there's an electric field that's related to the charge times this radial distance quantity. So in our case, a formula that's actually really quite useful is this one. And that is that the surface free charge density that's built up on here. So as the current comes in, there's a charge. And the strength of that is given by this formula here. So if sigma 1, that's the incident medium, is, let's say, it is less than sigma 2. So suppose we're going from a resistor to a conductor. So sigma 1 is less than sigma 2. So this number here is less than 1. If we subtract 1, then this is going to be negative. So that means if we've got a system like this, the current's coming in, then we've got negative charges on this side, and now we go from a resistor to conductors. That gives us positive charges. So that's a good mental image to have in mind. And now you can imagine that if we have a voltmeter or something up top measures electric field, then we'd be sensitive to those charges. Okay, so now let's look at a little bit more what's happening. So we've got a system where we've got currents that are coming in like that. So what we're looking at here is now a cylinder. So this is a buried cylinder, and we can make it conductive or resistive. But first of all, can you tell me by looking at how the currents are flowing, whether that is a conductive cylinder or a resistive cylinder? Pardon me?
Conductive.
And why?
But if you were conductive, point flow.
The current is trying to go inside it. If you just look at the shape of the currents, they are more dense inside the cylinder.
Yeah.
So it's like an easy patch to go inside.
Exactly. Exactly. So you look at this, see the current kind of like it's kind of drawing in here, kind of sucking up in there. So rather than the currents kind of flowing harmonically through there, they're kind of sucked in. So it's a path of
easier
resistance. So that's a conductor.
Yeah.
Okay. Now remember what I said with respect to the charges. Yeah. So we're going from something that's resistive to conductive. So there's a negative charge that's going to be built up here, and then the other way around, there's a positive charge. Okay. So here's our currents. Here's our charges. They generate an electric field. So we can generate an electric field. We call that, the fields from here are just called the secondary fields. So if there was, we're taking away any other of the fields. We're just looking at the fields caused by these charges. And you can see what they look like. There's positive here. So they, field lines would go from the positive to the negative out here. So it kind of looks like a dipole, right? It's like an electric dipole. Currents going out, in, out, in. And those currents are associated with these charges. These charges give rise to their own electric potential, and that's called the secondary potential, and it looks like this. So it's blue over here, so it's negative, and it's yellow over here, which is positive. So this is actually our signal. We're going to try to measure this guy. We're only going to be able to measure it at the surface, but that's our signal. It's the field due to all of these charges. So now let's take a little bit closer look to say, okay, we'd really like to find this the cylinder. So let's do an experiment where we set up a positive electrode here and a negative electrode here. So here's our A and B. The object that we're looking for is a 1 ohm meter cylinder buried in a background of 500 ohm meters. And now we're going to set up this experiment. Got currents flowing through here, and we're going to measure the electric potentials here, and we put that into our formula, and we get an apparent resistivity of 430 ohms. Okay, so that, first of all, is that good or bad? Luis? Nikolai?
The secondary current, so the second, if you can go, just go back one slide, please.
Back.
So the, yeah, this one. What we are actually measuring is the total fields or the total currents. Like this secondary currents is mathematically you're isolating the effects of this induced dipole. But what you do measure is the total.
Perfect. Yeah.
And this is just a mathematical.
That's right. So that's what this is the signal that we're ultimately interested in. What we actually measure. So here's the electric potential that we measure over the the sphere. So this is the total potential. Mm-hmm. Now we're going to measure at these two spots here. Put electrodes in here. We're going to get a voltage. Plug that into our formula, and we get 430 ohm meters. My question was, okay, are you happy with that? Is that a good number? Or?
It's a good number. It's not enough. You need many more measurements to guess what has produced it.
What are the previous measures?
Yeah. Okay, so fair enough. If we measure up over here, we've got 500 ohm meters, right?
Okay, so as we are
so as we're coming up, as we take our potential electrodes and we move them from here to here to here, so we have like 502 over there, which is about the background. Actually, it's a little bit more than the background, but won't worry about that for now. But that's what you're a long ways away from the cylinder. So basically, you're measuring the background, and then as you get over top, you dip down a bit, right? You don't go down to 100, but you're dipping down, and then over here. So you can see that in this experiment, if I had the currents out here and I just went over and measured potentials, convert that to apparent resistivities, Sergio is a conductor, come down, get down a bit. So that's the strength of my signal, and I'd say, yeah, maybe right over top here, there might be something that's conductive. So we have an app. It's a Gsi cylinder app, and we can use that to kind of address some questions. So let's just fire that guy up. This one. So this one's similar to what you had before, except that we have we've got a background and we've got a target, which is now a cylinder. So rather than being a layer, it's a cylinder. And we have the parameters. We've got the A and the B, as we usually have M and N. So those are always the same. And then we've got the radius of the cylinder, R. And then you can have a horizontal location and a vertical location at the center of the cylinder. And then we've got the resistivities of the half space and the resistivities of the cylinder. So that's the row 1 and row 2. And then we have a whole bunch of fields that we can visualize. So maybe, you know, as a first shot to kind of think through this, and it's a question that somebody often asks, and that is like, oh, can I find a buried tunnel? Okay. Often in karst regions, for instance, there's tunnels, or maybe there's a high conducting cylinder, big pipe or something that's going through. So there's a lot of things that you could kind of think about as to like, okay, maybe could I use DC resistivity to find this thing? Okay, so let's just kind of go through that. And let's suppose you're trying to find a buried tunnel. And somebody comes asking, oh, Roberto, can you find a buried tunnel with DC resistivity? What would your answer be?
I don't think so. Depending on the casing of the tunnel, and what is flowing through the tunnel. So.
Good. Okay, that's good. So it's going to depend upon the properties of the tunnel.
The properties are different from the surrounding properties.
Okay, good. Okay, so let's make a tunnel. Let's just try to do this. Okay, so first of all, we're a little bit limited here in the sense that we can go from minus 40 meters to 40 meters. Okay, and we can go from 0, that's in the horizontal scale, we can go from 0 to 35 down. Okay, so yeah, let's make a tunnel. What radius of a tunnel do we want?
5 meters.
5 meters, good choice. So it's 5 meter tunnel, okay, and now we come back to yours, like what's it filled with?
Air.
Air, okay, so air, resistivity of air. Pardon me? It is very high, yeah. So let's put resistivity, I don't know, we'll just add some zeros. That's big. Okay, but what about the background? Like if you were doing something out here, typical resistivity?
I need to go back to the tables that you showed us to take some numbers.
Josh, I'll help us. Typical resistivity, have you put a ohm meter DC experiment out there?
Tens of ohm meters.
Tens?
Tens, yeah.
Okay.
40, 50, up to 100.
Okay. Oh, let's make 100. 100 ohm meters. Okay. So it's outside, 100 ohm meters, and then we're going to fill a tunnel. Okay, and tunnel radius is 5 meters. We haven't said how deep it is yet. That might be important.
How deep?
Yeah.
5 meters.
5. Love it. I found it. Yes, it's just
a
kind
little
of
bit.
Well,
Okay, 20 meters.
Yeah, that's
Oh,
there we go.
20. That's 20 meters.
Oh, it was 20. Okay.
Mais barato arrancar toda a terra do que você construir um túnel 20 metros.
Okay. So first of all, is that okay for current if you're trying to find something like that? Do you think that's a good thing for the currents, or should we put the current someplace else?
Yeah. I think you more for it.
Well, we're just going to do one measure. We'll eventually do a whole bunch, right? But is this seem like a good one, or
You're asking about the place?
Yeah.
The position of the
A and B?
Yeah.
Okay, should we change?
A nice first try.
Nice first try. Good. Okay. So and then M and N. Good. 0.2.
Yeah. I think we should maybe to put M and N apart, and then start to moving the A and B close together, or the opposite.
I'll move the M and N.
Okay, make M and N what?
Closer
Closer together? Okay. Here, like that? Okay. All right. So we can change later, but let's just take a look at that. So you have a lot of flexibility. So see this region up here. So we could plot the model. So we can plot the model. That's what we've got here. We could also plot the potential, the electric field, currents, and the charges. Okay. And also the sensitivity. We'll talk about that later. Then we can talk also about like the total. We did that too, like with the total potential or the primary potential without things or secondary potential. And then the scale that we're working with could either be linear or log. So there's a fair number of ways in which you can plot, a fair number of things to plot and ways to plot them. So let's first of all kind of see if it looks like we're got a sensible survey geometry here. And the first way that I would do that is first of all look at the currents. So let's look first of all at the currents. We'll just look at the primary for a second. So let us look at just the primary currents. And here was our cylinder down here. So you can see that from the primary viewport, we've got currents that are going through. So that's good, right? That sounds like a good idea. And now let us look at the total currents and see how much those currents have been affected. So we can see how much the currents have been affected. And look at this, right? So now, here was our cylinder. It's resistive. So the currents don't want to go through a resistor. So they come and they kind of snake around, and they're just totally shunning, which is just the opposite to the conductive case, right? So when you see that, it's like, okay, that's looking good, because before I had something, now I put something in, and I get greatly distorted currents. So I think this is effective. That was a good choice. From the point of view of signal, we're actually interested in the charge. So now what I'm now going to do, notice that it is on total, and I'm going to click charge. So we're going to see the total charge. Okay. So before we click, and maybe this is the thing to work, how to approach any of these apps, and that is that, okay, I'm going to change something, but before I click, what am I expected to see? Right? So you could either get a picture in your mind, or you could draw something on the paper, but you need to commit yourself, like, okay, this is what I think is going to happen, because then that helps you, in doing that, you're thinking through the process about what's going on. And then you're going to click the button, and then either what you thought was going to appear does or not. If you get a picture out that agrees with what you had, it's like, okay, good job. Right? If you get one that disagrees, then A, you got to figure out why, and B, you learn something. So that's the process. It's not like, okay, I'm going to change something and click, 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 click. No, you got to be engaged with it. You got to be thinking about it, and that involves like anticipation. So here we're going to measure total, and we're going to measure the currents. or the charges. So first of all, what's the mental image that you're going to see?
Negative spot. Low charge spot.
Okay. Let's see. So I'm going to click this button.
Negative.
They're not there. At least it doesn't look like it. So what happened?
If it was a conductor, you have this induced charge in the boundaries of this. As it's isolator, very bad conductor.
What? Yeah, right.
Just to agree with the charge along the range, the model, but the total charge is zero.
Okay.
But
The
I think-
secondary would be that rearranging.
Tries
But I think you detected the tunnel walls. I think, didn't you?
No.
No?
No. Well, we didn't really see anything here. But if okay, so if
my position is if you change the conductance of the tunnel material.
Okay, so let's make the conductive. Let's instead of making it resistive, let's make it conductive. So make it 5 volts.
Sorry, before you to show the charge response, please. What are these dotted lines? The model what? It's the
Yeah, so the dots are showing where the cylinder was. That's where you had thought you'd see charges, right?
This is the real location.
This is the real location, correct?
Okay. Okay.
So that's just the model, right? But what you were saying is that we'd see, charges on the outside, right? Okay, so now, Roberto, you think that we're not saying charges because we got a resistor. So if I make that 1. There's my total charge. And now if we look at the currents, so you can see here how we're kind of sucking in. So that's what we had before. So it's sucking in. So just the same. So let's go back to the resistor. So here's the currents for the resistor.
Depends, you are putting the free charge or the induced polarizing charge?
No induced polarization. We're just talking about the free charges. Yeah.
Okay.
So you might think that there has to be charges here, right? Because I'm changing the currents from what used to be. So now they're going on. So that means in order to deflect these currents, there must be fields that are causing them to go around. So there should be charges, but when I plot it, I get that. Okay, the clue in here is the word total. Okay, so think about what happens if I have a battery or a generator. Okay. So if I put one pole of that battery here, what do I got? I just got a huge positive charge. So I got a huge positive charge here and a huge negative charge here. So if I look at the charges in the system, they're completely dominated by what I've got here. So there's a big value of charge here, a big value of charge here. So That's where really all of the charges are. But if I look now at the secondary charges, now I see something, right? So here's what you were expecting to see was the charges on here. Now,
you pull charges apart from each other, but the total charge is the same as it.
Right, so the total charge is so here's the primary charge. That's just like a half space and the electrodes hooked up, right? And the total charge is that plus whatever charge is built up on here. But that charge is so small on this big color scale here that we just really don't see it. But if I go to the secondary charge, then now I see it. So here's actually the charges that are built up on that object. And yeah, you'll notice also that we've changed the sign here, right? Because we're going from a conductor to a resistor, right? Remember, this is 5 million ohm meters or something. So migrate up to the outside of the cylinder so that you got the negatives over here and positives. So the net charge, okay, is negative over here and positive over here. Overall, that if you evaluated the total charge on here, it's 0. There's as many positives as negatives. So it's basically a separation then of charge.
But the migration of the electrons, free electrons, is within the cylinder.
Yes, yes. Yeah, because you've got, I mean, basically you've got all kinds of fluids in the cylinder. You've got free ions.
And you're talking about free charge here. It's not a polarized induced charge.
No,
it's actually
these are
charge.
actually free charges. So they're extra ions that are sitting there. I mean, basically, I mean, you can usually, generally your fluids overall are, and your whole system is kind of electrically neutral, right? And then now you start to put in a current through there, you realize that, oh, I got to have some more charges here, so I put some positives here, negatives.
Mm-hmm.
Maybe it might be interesting to, there's a number of things that you can do. Remember I talked about like no, I haven't. I'll talk in a moment about, or maybe, no, that's right. Pardon me. Yes, we had a 4-electrode system. When I first started out, I just said, well, we have a current electrode and a potential electrode, right? And that we call that a pole-pole system because there's just one pole. But if I take a 4-electrode system and I take one, let's say, current electrode, and I put it out infinity or at least a couple of kilometers out, and I basically have one active current electrode and then a 2 potential electrode. Right? And so that's called a pole-dipole, or if we reverse the order, it's a pole or a dipole-pole. And the other one is I've got a 4-electrode system. I got 2 electrodes, 2 potential, or 2 dipoles, current and potential. What is instructive here, I think, is looking at a single current electrode and a single potential electrode and noticing what happens as we move that electrode relative to a cylinder at depth. So let's do that. So we're going to go to a pole-pole. And so now we've got a current that's here and a potential that's sitting there. But notice the, well, we're back to our conductor here. So notice that the current electrode here, it's going to be putting currents out through this way. So you got the negative charges here and the positive charges here. But what happens if I move that current electrode? There we go. So if I move that current electrode, you can just watch how see how the charges change?
Like a compass, like it's following the
That's right.
direction.
So that's really insightful, right? Because even if I've got one target, Sergio, right? If my current electrode is here, I'm kind of igniting it in a certain way, right? There's negative charges here, positive. But if I'm over here, then it's the other way around. So it's possible to excite bodies by different changes in your orientation. So it's let's just move him up a little closer to the surface too. Okay, so here it's then even more accentuated. So here's the current electrode. So the primary currents then just go through like this. So you got negatives here and positives here. And I want to make mention of the fact that this is kind of interesting. If you look at the apparent resistivities, okay, it's actually 110. The background here was 100, and the resistivity here is 1. So there is no resistivity in that model that has got a resistivity of greater than 100, and yet the apparent resistivity is 110. So how do we understand that from this particular plot? Why is it that the apparent resistivity is actually larger than any resistivity that's there?
Interesting. The inductive charge, if you look at the field that it would create, it's like a field in the opposite direction. So maybe the effective total field is lesser than smaller than the primary field.
I think that was.
So maybe the total effect is like a more resistive medium.
I think you exactly got it right. Let me just show you one more thing, and then we'll come back exactly to the. First of all, let's put the M electrode on the right-hand side. So the charges don't move, right? So if I'm sitting here.
Yeah, now it's the opposite.
So now the apparent resistivity is.
Yeah, but then the field is aligned.
And it's because I'm connected to these negative potentials, which is in the opposite direction as the primary, so that electric field is decreasing, and that means that the apparent resistivity is going to decrease. So this is the case that you kind of tend to think about, right? So I've got a current over here. If there's a conductor, I'm going to get these charges, So now I should get an apparent resistivity that's less than 100 ohm meters, right? But if I now take this and if we move this guy over here, eventually it's going to get on this other side, it's going to be more influenced by these positive charges. And hence that was what causes the problem. So if I move it, so we can see how we're sliding down. Now we got 92. Now eventually at this point it becomes up to 100. So when he's sitting right over top, it's right about 100. And then as he gets over this side, it's more affected by these positive charges. And the apparent resistivity it increases. Okay. So there's a lot of insight that comes out of that. Sort of recapping, if you've got a conductive target or a resistive target, then depending upon where you are with respect to that current electrode, you're going to be excited in different manners. And then there's the aspect of measuring something.
I have a question.
Yep.
You could detect the position of the tunnel, because here's the tunnel, but you shot, but you measured across the tunnel, actually perpendicular to the tunnel. If you measure the fields in that direction across the tunnel, could you still detect the position? Because you put your electrodes in this direction.
Right.
But if you put this direction, could you still detect the anomaly?
Yeah, so if you have a current source, then you get this distribution of charges on the tunnel. Okay, so they're actually going to be large in on the so if I put a current in here on the intersection, okay, put a current in here, then we're going to be measuring. we were measuring along in here, right? So and so we're really nicely coupled with that. But on this tunnel here with this A-B configuration, there is a charge that decreases both in this direction and in that direction. Right? So if we measured any orientation of electric fields outside here, then we would still be sensitive to those charges, and we could go ahead and invert them, and we would still get a cylinder. In fact, what in the mining companies these days is, they're often looking for plates or cylinders, and they don't really know where these things are or what the geometries are, and so put in electrodes that hopefully excite something, and then you'll measure potentials everywhere. And each time you measure potential, it's got some relationship to the charges that are built up there, and then you move the current electrodes and measure things again. And each datum that you get has got some information about that conductivity.
But if you put your detectors in different directions, you have different responses.
That's true. Yeah, you have different responses, but that's where you need to have an inversion algorithm to kind of unravel all this stuff. Okay. So now we come to profiling. We had talked about sounding, right? So we're sitting here gradually making everything bigger and then going to greater depth. But now we actually want to talk about profiling. And we've got a particular idea about this already, right? Because if I have current electrodes that are really close together, okay, and then I've got sort of potential electrodes that are really close. So let's suppose here's my 4 electrode array. It looks like this, right? And my currents now are only kind of going into the into sort of like the depths of this depth. And now I'm coming along like this, and the only thing that I'm actually seeing is this top region. So if I plotted the apparent resistivity, I just have the apparent resistivity of the capacitance. Okay? But if I make things longer, okay, now I'm long enough that I'm actually sensitive to Sergio, right? So now my electrodes are like this, and I'm moving things along. Then now I'm starting to see you, and so I have a profile now that looks like this. So each profile length here, we'll see a certain depth. If I have bigger offsets, then I'm going to see deeper. So that means if we don't really know at what depth something is, then we might have to do like multiple scans and then try to put that together. So that's essentially what we want to do. And that means that in the end, we want to be working with data that are both kind of expanding and translating. So we do a sounding, which is expansion, and we do a profiling, which is a translation. So here's where that jargon came in with respect to surveys. So we had the Wenner and the Schlumberger. A gradient array, which you'll sometimes hear, is you set up current electrodes that extend way to sort of outer reaches, and then you've got a region inside. You just measure the potentials everywhere. Sometimes you can measure potentials in both directions. And then a pole-pole is one in which you just have an active current and potential electrode, a pole-dipole current and potential, and a dipole-dipole that looks like that. So those are just names, just try to keep track of what electrodes are important. For those that are familiar with well logging, basically well logging is exactly the same as what we've just been talking about. It's just the geometry has changed so that you're seeing you put everything in depth as opposed to running along the surface. So at depth, you could have like this would effectively be a pole experiment. So you've got a current electrode down here and another current return up there, and then potential electrode here and another potential electrode here. And you just simply move this system up and down your well log or your well here and just record locations of your current and your apparent resistivities. Or you could have this is effectively like a pole-dipole experiment. So you've got a current that's sitting here, your other current is way up here, and then you've got a dipole that you're collecting data with downpole. Now you can move the whole system. So the same principle, same physics applies. I want to take you just through on just how you plot the data, because sometimes plotting the data can be very insightful. I mean, in seismic, you end up looking at data. You make your final interpretations from data. Here we can't do that, but it's still very useful to just understand how to plot the data. So let's think about a dipole-dipole survey. And if you want to both move this and translate things on the plane and have all these data, then how do you plot it? Here's the way we do it. If take a 45-degree angle from the center of this dipole and a 45-degree angle over here, put them through, and where they intersect, you're going to plot that number as whatever your apparent resistivity is. If you now move this apart, move it up here, then the plotting point is going to be down here. And if you move it up here, then the plotting point. Right, so that means that you're going to get a plotting plane here in which numbers that are deeper effectively are somehow representative of things that are farther apart, and they're, somehow this is kind of a depth scale, it's sort of a pseudo depth. Yeah.
Do you have the same thing as a reciprocity in these measurements?
Yes.
Because if you move like this, you'll have the same points.
Yeah.
You expect the same measurement. Right?
Yes. In fact, that's sometimes used in the field just to check on how well the equipment is working or if the electrodes are fine or something like that. So just to show you how this is built up, what we're now going to do is show you a short movie here. So it's a dipole-dipole experiment, and this dipole is going to go progressively out, then it's going to plot this line, and then this current is going to move over, and then plot that, square, that. So you can see how the data are being generated here. And then it's contoured. So this is an image of your data, and that's usually the way things are plotted. Even in the marine CSDM, you'll see pseudo-section plots, right? And that's exactly how they're generated. You've got a transmitter, got a receiver, and they're plotted in this way here. This axis is often called a pseudo-depth axis. And sometimes it's got a number like n equal 1, 2, 3, which just tells you sort of how many dipole spacings you are away. But this is not really a true depth, and what's plotted on here are not really true resistivities. They're just apparent resistivity. It's a way of codifying your data. There was a time many years ago that people actually tried to interpret geologically what was happening from looking at those data, but now we realize that's very challenging.
How do you determine their point? I don't like from this dipole-dipole system. I don't really like. How do you determine their cross? Like, because you have an angle there. Like, how do you?
45 degrees.
Why is that?
Just a way of plotting. This is just a way of plotting your data. Right? You can't get too carried away with trying to make a geologic interpretation. But it does tell you something, right? I mean, here, there is definitely something there that looks conductive. Right? So, and these numbers are, are kind of sensible numbers in the sense that they're telling you upper and lower bounds of what the resistivities are. What is these kinds of things are tremendously useful as quality control, right? So you go out, you collect some data, plot them up as a pseudo-section, and then you'll find that, maybe you've got stripes that are running through here. Oh, it's a bad electrode, right?
First viewing of that.
Review your data, kind of getting an idea of what's, first crack. It's hugely, hugely important. With everything, whenever you've got data, you want to have some quick way of plotting out to do QC. They like, okay, is equipment malfunctioning or not? Pseudo-sections fall into that category.
So that's why you say it's not a true depth there.
It's true, yeah. So I'll show you an example of what pseudo-sections look like over certain objects. So here's a conductive block. So this is true depth, 75 meters. And this is from minus 100 to 100 meters. And that's a 10 ohm meter block. And if I do a DC experiment over top of this, then I get a pseudo-section actually that looks like this. So there's already noise added to this. That's why it's not completely symmetric. But that's basically what my pseudo-section is. And you can see that there's something in here that is got low resistivity. So there's a conductor down there. In times past, people would recognize like, oh, if I actually have something like that, I know there's supposed to be what they call pant legs. So a geophysical interpreter might look for something like that and say, oh, I'm pretty sure there's a conductor right here, and they'd go down and they drill. And sometimes they were successful. Okay. However, if we have an Earth model that's got some geologic bodies that are sitting up here, small distortions. So these are conductive bodies, so maybe it bits of graphites or clays or sulfides or something. They're highly conductive. The pseudo-section now looks like this. So there's your data. So your data are completely obscured by just all of the stuff that's coming in. And you can actually understand why that's happening, because remember, if I put a current in here in the ground, then the current is going to go through these little conductors here. That's going to build up charges on those little conductors. Those are going to give rise to big signals because they're so close to the surface. So everything gets dominated by this near surface stuff. And so the result, the data look like that. Can't make any geologic sense out of it. The other thing is that sometimes the data look sensible, but they're completely wrong if you go ahead and interpret it geologically. Here's an example. So there's a variable overburden, resistive, conductive over here. There's a valley coming through here. And then there's two conductors that are sitting like this. Okay? So now we go ahead and we do our DC experiment over top of this. And we get something that looks like this. So when you first look at that, you think, oh, wow, that looks pretty good. It looks like there's, you know, a big conductor down here, right? And so you might think, okay, I'm just going to drill right through here, okay, and get this done. However, if you do drill right through there, that puts you right through here. So you missed it. I show you these because these are now illustrative examples that say, okay, plotting the data, pseudo-section, okay, it's good, but you're not going to make a geologic interpretation. For that, you actually need to do yeah, I just want to maybe we'll do the app for the pseudo-section. Because there's a couple of things here that are, again, noticeable. So in this app, again, we outline, so here's the pole, and where you plot it. Pole, dipole. So if you ever have a dipole, you tend to kind of go to the midpoint and then plot it down. Kind of a detail, but that's sort of how it works. And there's the plotting points for your. This again shows. So what we're looking at here, so here's a current, and then you got 2, 4, 6, 8 potential electrodes that you're going to use. And now here's when you do that intersection, then you plot the apparent resistivities along that line. And if you go over, like, so that would, now you move everything over one. So it's kind of like seismic in that regard. Like you've got sort of, you can think of a cable, got a source, transmitter, now you move everything over, dot, over, dot, 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 dot. So that's, bring that over. Okay. The thing that makes this interesting is that what we're going to do is we've got a cylinder in here. So just the same as we had before. In this case, it's the background is 1,000 millimeters, the resistivity is 50, and we've got horizontal location and a vertical location of the cylinder, and we've got a radius. Now we want to do different surveys over top. Okay? So we only got one model, there's just one model, but now if I do different surveys, I'm going to get different answers out as far as what the data look like. So let's just do that. So first of all, we could do a pole-pole, which now looks like this. So pole-pole is going to be, it's going to give you symmetric data over that cylinder. But now what happens if we do a pole-dipole? Right, so now remember how things change depending upon what the transmitter was. So remember, if Sergio was the conductor, if the transmitter is sitting here, right, you know, then he's got that negative charge there, and then it comes over here, and then it comes over here. And if I'm always just measuring to the one side, then I get out a particular kind of number. So if I look at a pole-dipole, actually looks like this. So notice, even though the Earth model is symmetric, because I've got sort of an asymmetric measuring my survey, okay, I do not, I get sort of an asymmetric data set. And similarly, if I go the other way, if I reverse the orientation, so now if I put the current electrode on the right, so now things reverse like that. And if I do a dipole-dipole, I'm back to symmetry. Okay, so there's one Earth model, but depending upon how I collect the data, my data might look quite different. The thing that's interesting about these, if those 4 different intersections, if I put them into an inversion, they all come out with basically a very cylindrical body in a background. Okay, so let's just take a quick look at that. So we'll talk a little bit more about using the apps, but the inroads to it is given by this website, and we'll show you how to run these and how to link them up with Binder. We'll do that in a bit, and there'll be some questions. So I want to just skip right to the inversion part now. So we've got pseudo sections. Realize like, okay, we can't get information from them. So let's just go to the inverse problem. I'm not going to tell you how we actually go ahead and do that. We'll have some of that on Thursday. But for now, here's the procedure. We can measure data, and then we can go ahead and invert that. In general, kind of what we're doing is if we have a two-dimensional system, which we're assuming that we have here, then we'll take the Earth, divide it up into a whole bunch of cells, so each kind of cylindrical cells, and then we will adjust the values of those so that we not only fit the data, but we also find out have a solution that has got some smoothness to it, that's close to a background. It's got some geologic information in it that when you look at the final section, you think, okay, that's reasonable or that's geologic. So let's just look at those three cases when we had the buried prism. Here's what the prism looked like, and here's what the pseudosection looked like. If we go ahead and we invert those data, we get something out that looks like this. So it's a high conducting block, or high conducting object, centered at the right location, at about the right depth. We do notice that it's not a real block, but things are transitioning. It's similar to what I showed you before, but that's because we're looking, that's what we're asking the inversion for. We're asking for some kind of smooth representation of the Earth that fits the data. And if you do the predicted data from here, you get that. So that's a good fit to that given the noise. So now let's look at a more challenging example. And that was this one with the geologic noise that was attached to it. So remember, here was the data set. Can't make any geologic interpretation from that. But if we take that and we invert it, then we get this. So the great thing about this is that we not only see the conductor that we're looking for, but there's actually all these other stuff out there, that's there, right? That's in the Earth model, and we've been able to discover it. So that might just be geologic junk that you don't care about, but you've recovered it, but actually maybe there's something interesting. So I think that's the really good news about this. You take these data, totally uninterpretable, invert them, and you get out an image that looks like this. And the predicted data from that are this, so that's a nice match. Okay? The last example that we had was the one with the valley. So we had this example here. There was our pseudosection, and now here's the kind of recovered resistivity from the inversion. And now you definitely see you've got two conductive bodies that are coming in. We don't see the bottom part here because we just don't have currents that are going down deep enough. We don't have that resolution, but we've got that top part nailed in pretty nicely, as well as there's a conductor. So the take-home messages here are kind of multiple. One is that the pseudosections are great from the point of view of QCing. Don't invert or don't make geologic interpretations from them, but there are inversion algorithms out there that can take those image data and construct something that's geologically useful. Okay, so what's the next step? Well, let's now get more into where we are with the real world, and maybe it's 3D. Everything that we talked about so far is absolutely valid, but in 3D things get more complicated because we've got a target and it have varied size, varied shape, depth, and we've also got backgrounds that could be really variable, right? So we got host rocks that could look like that. We could be have all kinds of topography. So things could get complicated. And so now you have this question about, I'm faced with trying to find, let's say, an ore body that's in a mountainous region like this. Okay, where do I put my currents? Can I collect everything in 2D or 3D? These are some of the same questions that you have in seismic, right? Can I get by with 2D or do I need a 3D seismic? Same things here. And then, which measurements? Because we can have E fields or B fields. And what are the effects of topography? So these are all really questions about survey design, right? Like how I've got something there, how do I generate a geophysical survey that is going to be sensitive to that? And sensitive is the right word. So I'm going to concentrate a bit on the word sensitivity. So first of all, let me ask a question here of, if I put up the word sensitivity, what would your definition be? Luis, do you have a... Yeah, I say sensitivity. What kind of springs into your mind as far as what I'd be talking about, or mathematically what's going on, or definition?
How sensible is something is sensible to a physical property.
We have to distinguish different patterns.
I would say how big is the response of a specific reading of an instrument related to a change in a specific property.
Yeah, that's very good.
Contrast.
Yeah, you have a, let's say you got a body, okay, and it's it's characterized by certain parameters. Maybe it's the velocity or density, or and you want to know if I change that velocity or density, what would be the change in the data? So here's just a generic kind of definition for sensitivity. It's sort of like a change in the data with respect to a change in a model parameter. So whether you're translating something or changing its value or whatever. So that's sort of the sensitivity. It's a good definition. If we're actually going to kind of think through what sensitivity means, then it really falls into two parts. One is, first of all, exciting the target. Okay, that's the main thing. If I'm going to try to find Sergio, I bloody well get current through him. I really need to excite him. That's the first thing. And then the second is, once he's been excited, then I need to have a device that measures measures his response, and I want to find something that is as good as possible, and have the largest amplitude and maybe right component. So let's just kind of work through that. We've got exciting the target. We talked about that before. We've got currents that are kind of going through it. You can see this body is being excited by these currents. So currents going through and also being distorted by that. So that's good. The charge and the secondary currents were something like that, and the charges were like this. So the fact that I've got substantial charges that are built up, that's good, right? So we're exciting that body. And then there's the measurements. So now we can think about, okay, I've got a body that has been charged up. What do I want to measure? Well, it's kind of intuitive that you just want to have a potential electrode that's as close as possible to those charges. Right? So ideally, you probably want to have electrodes down here. That'd be good. But if you can't, if you're stuck to the surface, then measuring along the surface along here would you're close to the charges. So it's kind of intuitive, but that actually works well for any kind of experiment. You need to be able to excite the body, and then once you've excited it, have an instrument that measures the right kind of field as close as possible. The one thing we haven't touched very much on at this point is something called coupling. So we've got, let's now consider a plate. So we have to consider cylinders, but let's consider a plate. And if we've got an A electrode and a B electrode, so we got currents that are going through this way. And we can see that, if we put the plate in, there's currents that are going in. See how they're being sucked in a bit? So we're definitely exciting the target. But if we took that plate and we laid it on its side, and then we look to see what the currents are, we see, wow, those are actually quite different. So it's not only that we got a plate, but it's how that plate is oriented with respect to the to the primary field. So again, those are the same kinds of things you'd have in seismology. You're trying to find something, right? So it's how that something interacts with your primary field that's important. But here you can see it because of the currents. So that's the plate. Let's say the other thing we haven't talked about at this point yet is, okay, I got a plate, but is it a conductor or a resistor? We showed it with the tunnel, right? Had both a resistive and conductive tunnel. You see that they both kind of showed up. But what happens? What do you think is going to happen with a plate if we make it conductive or resistive? With respect to, do you think one is going to have a better response than the other, or the response is going to be the same? Or
just a guess. It's more resistive. The plate material has a higher resistivity. I think it will be easier to find it.
I'd say that's a good guess. So perhaps the intuition is kind of coming from here. If we have a conductive plate, it kind of gets fused. Yeah, you did. But if you have a resistive plate, it's got to flow around, right? And so if we look at the charges that are kind of built up, there's still charges here, but there's actually about a factor of 5 difference. And notice here, so we're going into a conductor, so we got negative and positive. And now we're going into resistors, so we got positive. And so, yeah, so bigger response actually from the resistor, but you can see the both. There's an app that we have that you can play around with and look at the charges and currents from a plate, and we'll postpone that to later. So in summary, I just want to mention when we're talking about survey design and looking in particular at sensitivity, 2 parts. First of all, exciting the body. It's always the first part to think about. And then the next is what instrument you're going to take and what the orientation is. I find that, in a way, this is kind of intuitively simple how you think about it, but a lot of people get very involved in, like, okay, I've got this problem, what's my sensitivity to finding this? And they couple in both the source and the receiver all in one, and then they look at the sensitivity function, for instance, okay? But the sensitivity function is actually composed of 2 things. There's an excitation, and then there's an observation. And if you break those things up, you get a lot more insight. So it's a very simple thing, but it's very effective in how you kind of think about the problem and the effectiveness of a particular data. So that's for our survey design now. There's first thing that you have to ask is, okay, what's my objective? If I've got a layered earth, okay, that's no problem. I can just do a 1D sounding, whether Schlumberger or winter. If I've got a 2D earth, okay, then I can do that kind of profiling and sounding that we have talked about, and that's no problem. If I got a 3D earth, well, things are more complicated, just as they are in seismic, right? Because you really need to have 3D coverage, and that means multiple transmitters, multiple receivers in order to really get what's there. So that again now comes back exactly to the problems you're faced in seismic. You would not want to try to find a 3D body with just a single towed streamer line of data. The other thing it's important, we'll come back to this a little bit later, is like what's the background resistivity and what are the effects of that? And then there's other things that come into play, noise sources, fences, power lines, etc. I just want to conclude, and then we'll have lunch. I've got couple more slides. But with respect to survey design, this is actually a challenge that everybody faces in geophysics, and there's really no simple answer out of it. You really have to look at a problem by problem basis. What's my geology? What is the geometry of the object that I'm looking at? And postulate particular transmitters and receivers and just see what you get out. In general, here's the idea. So we've got a 3D geometry here. Maybe we've got background geology and some conductors that are sitting in here. And then to see if a particular datum is actually going to be useful, we would go ahead and put on a particular survey over top of this without the object. Okay? And that might give us a baseline. So let's suppose this line here is without the object, and then you do it with the object, and you get out something that looks like this. So it's different, without, different. And then you look at what this difference is and try to decide, okay, is that significant? Is that something that I could see or not? And so you look at that magnitude, and then there's usually two things. One is it greater than a certain value, greater than 4 value, or is it on a percentage basis, is it large compared to what the primary is? Because very often your data, when you're assigning errors to them, there's like maybe a percent error, like maybe it's 3% or whatever, right? And there might also be a floor. So that's the reason for it. So that's a good place to quit for lunch. So what we'll do after lunch is come back and look at a couple of case histories and kind of went over. Okay. So what do you guys do for lunch?